All right, it's Tuesday. Hello, welcome again to part 7 of this. Lots to get through today, so I am going to get stuck into it right now. What am I doing? I'm making a WebAssembly interpreter in Ruby. I've been doing that for a while now. Probably going to be continuing to do that for a while yet. Um, I'm doing that to have fun. I want to demystify WebAssembly. I want to share how I actually approach this project. I want to have fun more than make something functional. I want to make something correct before I make something that's fast. I want to make the code nice and clear, even if it's not very clever. I'm still trying to do it in pure Ruby. I think the rubber is going to hit the road on that today. And I'm trying to do it without any dependencies. The rubber is also going to hit the road on that today. So that's where I am. Quick retro before I begin. So last time I had some internet problems. My broadband connection died just as I was wrapping up the last stream. So I'm very sorry if you watched it. I'm very sorry that it cut off so abruptly at the end. That was not by design. It was, frustratingly, I'd been saying for hours that I was going to take a look at Afuk's pull request, and then just as I began to do that, my broadband went down. So I'm sorry about that. I'm particularly sorry to Afuk. I'll start with that today. I'll start where I left off. But that was unfortunate. But I suppose, well, it doesn't feel like there's anything I can do about it. So such is life. Still working on floating point numbers. I got quite a long way with floating point numbers, with the conversions of floating point numbers yesterday. But I did end up getting stuck on something where the way that Ruby encodes floating point numbers, specifically 32-bit floating point numbers, does not agree with what WebAssembly wants to happen, and I couldn't see any way to control that. I'm slightly apprehensive about just implementing that encoding myself, but also I think it'll probably be fun, at least for me. So I'm sort of also looking forward to it, even though I slightly dread it. So that's really what's going to happen this time. I'm also aware that the code is getting really messy now. Like I said last time, it was starting to get messy. I just jammed in loads more code last time and didn't really do any refactoring. So I sort of desperately need to take a breath and do some refactoring. However, I am going to continue resisting the temptation to do that because, it's red-green refactor, right? I at the moment, I've got a failing test that conversions.wast. So I'm going to wait until that file is passing, and then it'll be cleanup time. I'm hoping that maybe the next stream that I do after this one can just be a huge therapeutic refactoring session in the sort of Katrina Owen vein, where I just sweep all of that junk into neat little piles, and it all kind of boils down, and 90% of it is incidental complexity that evaporates. That'll be very satisfying. I'm just conscious that if I start doing that now, I will be further delaying the point at which I've got a working implementation of floating point numbers. So I'm kind of just trying to stumble across the finish line here. At least that's what I've decided I'm going to do, is stumble across the finish line. So that's it. I think there's going to be a lot to do, so I might as well get stuck in now. I did say that... What was it here? Oh yeah, I'd started looking at the spec compliance suggestions from Afuk's PR. Oh, hi Afuk, welcome to the chat. I hope you are feeling well today. Let's take a look. Oh, I think I've actually already got it. I've pre-opened this so that I can get it in while my internet connection is still working. This was the pull request that Afuk kindly sent. I somewhat stubbornly didn't look at it because I was very curious because I wanted to understand how much of the content of this PR was ultimately going to be necessitated by the executable specifications versus stuff that they hadn't thought of covering, and it was just stuff that was obvious to Afuk but not to me that needed to be done to make the implementation sensible. So what Afuk says is it fixes some general spec compliance problems with respect to floats. These have not yet come up in any of the tests, bearing in mind that he wrote this before yesterday's stream, where I think some of these issues did come up in the tests. So things like capital letters, I mean, this is all case sensitivity, right? Capital hex characters and capital exponent separators, exponent delimiters. Oh, fuck, did you? Oh, it says new changes since you last viewed. I don't know if that's true. It's very hard to know whether GitHub is telling the truth at any given time. Anyway, probably not. Right, let's have a look. So the first one, makes sure to match all hex characters. The spec states that hex digit can have uppercase or lowercase hex characters. Yeah. Oh, okay, well, yeah. So you didn't push anything. It's just GitHub being confused as usual. Right, okay. So, yeah, this is kind of similar to what I did, right? But how do I get this? Yes. So I did the less clever thing of just expanding the character class, but it has the same effect. Something that Afuk mentioned to me offline, but still through the internet, is that I made a choice here. In fact, I think the commit after this one, I thought I was being clever, subbing in these POSIX bracket expressions to stand in for hex digits and numerical digits. That may perhaps, or let's say almost certainly, not have been a good idea, but I'll return to that in a second. Okay, so this is, I think I did this, and because I had to make a test pass. Right, this is right. Okay, so this isn't changing the behavior at all. This is just making it more readable. I agree. That's a good idea. I think maybe I should go back and do that actually. And then finally, right. So you made basically the same decision as me here. You use slightly different syntax, but you made the same decision to keep the regular expression case sensitive, but just make the exponent delimiter case insensitive. So I think I'm right in saying that that's all stuff that I have done. It's very interesting that you anticipated these problems in advance of the tests requiring them. I mean, I suppose what I really mean is I also should have immediately recognized that this was going to be a problem and that these need to be case insensitive, but it didn't occur to me when I was writing the regular expression. I wonder if I'm being too, I'm sort of, in a way, I'm sort of trying not to think about the problem space very hard. I'm just kind of grinding through making the test pass, and this is a good reminder that maybe I should actually think about what I'm doing. So I think ultimately, because of my pig-headed refusal to look at those changes before I did this last stream, I think that those changes are all already done. But the thing about regexp, the thing about the POSIX bracket expressions, yes. The point Afuk made is that these encompass non-ASCII characters. For instance, \d matches only the ASCII decimal digits 0 through 9, whereas digit matches any character in the Unicode ND category. And I think if I don't want to get too bogged down in what that is, but I think just searching for it will indicate that these are our friends, the sort of normal ASCII digits. And then there's, you can see by the size of the scroll bar, rather a lot of other digits, which are less familiar to me, but nonetheless are sort of lexically categorized as being digits. Now, I certainly didn't intend that it be possible to use any of these digits, not least because I'm ultimately relying on string to integer to be able to interpret these. So I certainly didn't mean to include all of these slightly more unusual Unicode digits. And I think you're right, Fook, when you say that this is a little unclear. X digit, it says digit allowed in a hexadecimal number, i.e. 0 to 9 A to F, A to F. So that's actually a little bit, that's strange. That would suggest that actually X digit is probably okay. But it's not particularly helpful to be using a bracket expression for X digit and not using one for digit. So I think what I'm going to do is remember how... I'm like looking for a dingus that lets me copy the SHA of this commit, but I think I'm just going to have to copy it like that. So what I'm going to do is... I think what I'm going to do is replace this with... I'm not sure what the escaping rules are here. Probably that. Yes, I remember last time I got this wrong and I've just got it wrong again. Probably escape these. Yes. And then also... Is it hex digit with \h, or is it h digit? Can't remember. I was literally just looking at it. Of course, X digit. Why didn't I remember that? That's very sensible. Okay, so that's essentially reverting that previous commit. But let's check and see what the deal is. I.e., does everything still work? Yes. So that hasn't broken anything. So what I'm going to do is just say switch away from POSIX. What did I say here? Yeah. Switch away from POSIT bracket expressions for decimal and hex digits. So I'm just going to write a quick message there that says I introduced these in that commit because I thought they were slightly easier to read and understand. But Paracycle pointed out that at least digit and possibly X digit matches non-ASCII digit characters, which was not my intention. It's therefore more correct to use \d and \h to match decimal and hexadecimal digits, respectively. Okay. Cool. All right. Well, thank you very much for your help, Fook. I really appreciate you giving me this thoughtful code review. Yeah, I really don't know what to do about these regular expressions. I think I'm beware Unicode, hex digits per Paracycle. I think I'm just gonna not look directly at the regular expressions for now because they're sort of an attractive nuisance. So And I'm going to also check this off as won't fix, because I think what we've learned is that we don't want to use those POSIX bracket expressions, at least not for digits. Right. Lots of tempting rubbish in here. I think I'm gonna just ignore it and get stuck right back into what I was trying to do last time, which was make these conversions work. So this was how far we got. Convert I64S. So this is trying to... Right, so this is F32 convert I64S. In fact, why don't we find the actual test that is failing here? WebAssembly spec conversions.wast, and then it's f32.convert I64S. So that function is defined once, but it's called a bunch of times. I can't remember exactly which one of these is failing. Is this 341? Oh. I should make this print it out, shouldn't I? I feel like there's another thing here to sort of improve the debugging output. But somewhere in here, oh, it's I32S, not I64S. Okay. Those are the I32s. It was the I64 that was causing the problem. Yes, because yeah, this is right, because there's a 0 is the third one there, and there's 0 here, and then after the 0, 7 more. 1, 2, 3, 4, 5, 6. So it's this one. Test rounding directions. Expected blah got blah. So these are only one different. So I assume this is... I haven't really verified this, but I'm just going with my gut that this is almost certainly just, and especially given that this is the test rounding direction section, this is almost certainly just not rounding in the way that WebAssembly would like it to. So yeah, the way I wanted to approach this, for better or worse, is to start implementing the code that can take essentially any rational number and turn it into a bit pattern representing a 32-bit or a 64-bit float. In yesterday's stream, I went through in some detail an example of how to do that, and I used pi as an example. So I sort of started with this quite specific value for pi, and then I worked through converting that into a single precision, which means 32-bit floating point number, and we got the right answer at the end. So I won't repeat that now, or at least not concretely. I think what I am going to do is repeat it abstractly, sort of go through the process that I did here to convert a floating point a rational number into a float, and just write that down as Ruby code. And then I'm sort of hoping that this line of code, I guess it's this line of code that's problematic, or like really the combination of these two lines of code, that like I'm taking an integer Yes, I'm taking this 64-bit integer and I'm trying to convert it into, by which I mean find the nearest 32-bit floating point number, and it's not doing the right thing. So I'm hoping that instead of these two lines, so let's say here to do, replace this with a call to something. I have written. So rather than relying on packet as a 32-bit float and then unpack it, I'm hoping that I can just write some code that says take this value and then please return me please return me a 32-bit float that is as close as possible to it. And you know, we have at least, well, I guess this is one test case here. And I've sort of got another test case here, which is doing it with, you know, this value of pi I started with is too precise to be expressible as a 32-bit float. And so the final value we get is not exactly the same, but it is, I believe, the correct, you know, closest representation of pi. So let's just do that then. I think what I'm going to do, because I'm becoming so concerned about this file becoming very long and very messy, and also because I think it would be quite useful for me to be able to write unit tests as part of this process, I'm going to break this out into another file. So I'll start writing in, let's just call it float.rb. Well, this is going to be problematic because there's a top level, there's a top level class called float. So let's put this inside a wasminer. This is what I'm thinking. I want basically a module function called encode that takes some arguments, and then this is just going to go through this process of encoding it, and it's going to return an integer that represents the encoding as, oh yeah, well this is going to take a bits argument, and then it's going to return, if you ask for 32, it's going to give you back a 32-bit integer that represents the encoding of a 32-bit float. Which rather implies that this code here, well, firstly, I'm going to need to require float at the top here. And then down here, I'm going to have to call wasminer float.encode something. Is this right? Yes. Bits here is the size of the float that we're trying to get. So F32 or F64. So that's correct. Well, we are going to need, you know, integer equals signed value bits, integer bits. So like that part of what I had there is going to be needed. But then this bit is, well, I mean, I guess I'm doing this now. That to do is being done. So the integer bits goes there, and then this is going to be something. I'm just thinking about what I want here. What do I want? I think what I want is, so just thinking about what I did last time. So I must admit I'm thinking ahead a little bit here. Like I said, I think the method I went through last time is essentially the method for turning a rational number into a floating point number. So sort of essentially the input that I started with here, although it was 3.1415926 blah, that was expressed as a rational number. So this large integer as the numerator of a fraction whose denominator is 10 to the 15. So I think I'm just going to do this to keep it simple. I might regret it. Like, I don't really need this at the moment, but this was what I did. The example I went through, I sort of started with some numerator and some denominator. So to sort of just implement this, I'm going to need the numerator and the denominator. In this specific case, I know that the numerator is just whatever integer I've been given. That really didn't save me any typing at all. And the denominator is just going to be 1. So this denominator argument might be completely surplus to requirements. But A, I'm sort of expecting it when I write this algorithm here. And B, I must admit I'm thinking ahead slightly here. If I can get this working, then this is a very useful general operation to have, because it means that I can take something like this as a string or something in scientific notation, and then turn that into a numerator and a denominator. So if this is, well, if it was just this, then this is this big integer times 10 to the minus 15. I can turn that into 10 to the 15 as the denominator, and then this large integer as the numerator. So I think keeping this generality or having it available to me is, if this succeeds, I might be able to replace all of my floating point operations with this encoding. So I'm going to give myself the option to do that. And if I end up just removing this denominator argument and changing numerator here to just like integer, then so be it. But this is going to make it easier for me to think about. So I think this is what I want on the calling side. So that's, that's easy. All I've got to do now is fill in this. So what are the things that I'm going to want to do here? So, right. So essentially the first thing that we need to do is, well, the first thing we needed to do with pi was to scale this up into the right range. And so I need to know what the range is. So it's like determine the fraction. Determine the range of valid fractions. So what I mean by that is the number that we can write here. In the case of a 32-bit float, it's important that it's really not the fraction, it's the significand. Just call it quotient for now. So if we want it to be a 24-bit binary number, then we know that there's a minimum and a maximum that can possibly be. So in this case, it was 8 million and change and 16 million and change. So we've got to calculate that. I don't know if I said determine. Calculate the range of valid quotients. Let's call it significans, because that is actually the right word. Okay, and then scale the quotient up, well, or down until it's in range. So that means in this case, this meant modifying the numerator to make it larger so that it was in this range, depending on what the numerator and the denominator here are. We might need to scale it down to get it into range. So this is gonna, chances are that doing numerator divided by denominator is going to give you a number that is either too large or too small, and we're going to have to nudge it up and down. So then once we've done that, rounding, round if necessary. And we can cross that bridge when we come to it. Adjust the exponent well to account for scaling, I guess, and then adjust the exponent to account for, I'm just going to say significand format. Maybe I'll say normalized. What I mean by that is that the significand is written in this specific format. So you have to put a decimal, well, a radix point after the first digit. So when I did this conversion last time, I had to adjust the exponent to account for the fact that I generated this 24-bit number, but it was 2 to the 23 times larger than the number that was actually written in the float format. And then what? Oh yes, add bias to exponent. Again, I talked about that at some length last time, but for now I'll just say that because exponents can be negative or positive, the way that they're encoded in IEEE 754 floating point is that you just add a predetermined amount to them to make it into a positive number, and that's pre-agreed. So when you're decoding one of these, you have to then subtract that number again, this bias, in order to recover the real exponent. And then I suppose assemble bits into float. Like, that's pretty much it. Well, can I just crack on with that then? Is there any reason why I can't? I don't think so. I think I can just get on with it. So the reason I'm hesitating is that I'm realizing that I don't know any of the numbers that I'm going to need here. What I want to write here is something like minimum significand equals, well, I know how many bits it is. If I knew how many bits it was, then it would be well, it would be something like this, right? I would when I knew that I was looking for a 24-bit binary number, the smallest number that requires 24 bits to write it out is 1 followed by 23 zeros. So you have to subtract 1 from the significand, and then shift a 1 up into that position. The max significand is like a subtraction in a different place. The largest 24-bit number is this 1 shifted left 24 places is actually the smallest 25-bit number, and then if we subtract 1, we get the largest 24-bit number. So this is significand bits 1 shifted left by the significand bits, and then we subtract 1 from it. So we're writing almost the same expression twice there, but with the brackets in a different place, which makes it mean something, but means something different. But of course, the problem here is I don't know what these are. So what I'm going to have to do is say what significand bits is. So I'm going to have to say significand bits equals, well, let's say case bits in 32. What am I trying to make work here? I'm trying to make 32 work, right? Yeah, bits equals 32. So I'll just concentrate on that for now. So in 32, the number of significand bits is 24. Let's find a reference for that. IEEE, not 3, 754. Single precision. Not right now, Jimmy Wales. You'll have to survive without me for a minute. So yes, 24-bit significand, 23 explicitly stored. So the significand includes this kind of hidden bit, this leading one, which we're going to include in the number we're generating here, and then just this final step, when we assemble the bits into the float, we just don't write that one in because it's implicit. So yes, I realize that this isn't really doing anything except it's sort of gating this, sort of guarding this function. If anyone calls it with anything other than 32 bits, which I don't know how to handle at the moment, that's going to raise an exception, which is what I want. Okay, so that is the range of valid significands. Scale the quotient up or down until it's in range. And what I mean by that is this quotient I'm talking about is the... Just trying to work out whether I want to use the word quotient here, because it's... I think I'm just going to use significand all the way through, because even though it is the quotient, it's... What I mean is this is the ratio between the integer ratio between the numerator and the denominator. So in this case, this huge number divided by 10 to the power of 15, the ratio is just 3. So that's kind of a very clumsy approximation to the number that we're trying to encode, but it's not a very good one. It's missing out all of the juicy details of pi. So the goal here is to make a bigger number than a bigger integer than 3 that contains more information, and just remember how much bigger it is than the number we actually need, because when we encode this as a float, we can include in the exponent, we can say, oh, you need to halve this 20 times or whatever in order to get to the number that we're actually trying to express. So so this is gonna, what we want to do is, okay, I'm just going to think this through. We want to have a loop here. I'm not sure. The reason why I'm not immediately writing a loop condition is because, well, what I want to say is until, min significand up to max significand includes this numerator divided by the denominator. But if it doesn't, then I immediately need to know what the what the result of this division is, and I could put an assignment inside here, but for now I'm just going to try this, and then I can always break out of this loop. And in fact, now that I think about it, that's actually rather nice, because what I want to do here is sort of say, if it's too small, then scale it up, else if it's too large, scale it down. And then this is the kind of Goldilocks, like, it's just right. Like here, we're just going to break. So actually, the fact that there are 3 different outcomes that we want here based on the value of the significand, I think it's actually kind of nice to be able to put this in the else clause, because it's just like, if you fall through these 2 checks, then you're done, rather than trying to cook up a big sort of compound condition whose component parts you're going to need to know about anyway. So so what does this look like? If it's too small, so if significand is less than the minimum, and while I'm doing that, let's say if it's larger than the maximum, so scale it up means that we're going to make the numerator larger. So that means the numerator is going to be multiplied by 2. We're going to shift it to the left. If we want to scale it down, then that means making the denominator larger. So we're going to scale the denominator up. And if it's just right, then we're just going to return. So actually, for now at least, I'll leave these comments in. I don't really like writing comments in code. I would much rather, in this case, I'd rather like extract a little method whose name explains what this is doing. I think having a comment there is just a bit not particularly helpful, but let's see what happens. I think right now it's useful mental scaffolding for me to have this here, and maybe I'll leave them in if this ends up just as being one long method. So I'm conscious I haven't executed this code yet, but like there's no point in executing it until I've got something here, and then we can see what happens. And I think I am going to want to write a little unit test for this rather than call it through the acceptance test. But I'm just trying to flesh out my sketch before I run it for the first time, and then we'll actually properly engage with the question of, does this code actually work and do what it's supposed to? Round the significand if necessary. Do I want to do that now? Yeah, I mean, I might as well, because it's not that difficult. What you do is take the remainder of this division, so numerator modulus denominator, because I've already got the quotient that's in the significand, and we say if the remainder is greater than the denominator over 2, then we just round this up. So what that means is this, what's going on here is that if I do 199 over 100, I get 1. But the remainder of that division is almost as large as the denominator itself. Specifically it's larger than 50, so it's in the top half of the denominator. So arguably a more accurate answer to this question in the presence of rounding is 2. The closest integer to what do you get if you divide 199 by 100 is 2, arguably. And so that's why we want to add 1 to the answer if the remainder is larger than half of the denominator. So that's what I'm doing here. I also need to think about to do break tie. Because the rounding behavior, where's the default? This doesn't say. I think that the default rounding behavior is rounding to even. If I search for even. Yeah, I mean, this just doesn't have that information in it. I expect the WebAssembly spec does. I mean, this is what we really care about. It doesn't really matter what the IEEE 754 standard says. I'm going to guess execution. Floating point operations. Does this... Yes, all operators use rounds to nearest, ties to even. So what all that means is, I mean, maybe the clearest way is to just implement it. What I'm going to say is we're going to round up when it's clearly the case that the remainder is large enough to justify it. But there's the other case where the remainder, not remainder, is equal to the denominator divided by 2. And Well, okay. So yes, if the remainder is exactly half of the denominator, then this round to even rule is like we've got a tie break situation now where it's like, well, you know, in this case, 150 divided by 100 gives me the answer 1. Now, the remainder is exactly half of the denominator, so who is to say whether 1 or 2 is the closer answer in this case? And this round to nearest ties to even behavior is saying we break a tie, which is always going to be between two consecutive numbers, one of which is always going to be odd and one of which is always going to be even. It just says prefer the even one. So in this case, we would actually round it up to 2, whereas if I was doing 250 divided by 100 and the answer was already 2, then we break the tie between 2 and 3 by again picking 2. So this is just... I don't think it's very mathematically significant, although I don't know what I'm talking about, so I don't know why I said that. But to me, it's just a way of being consistent. Like, let's just make a rule so that everyone can do the same thing. And the rule that this spec uses, and I believe this is the default for IEEE 754, is just this ties to even. So in this case, if we've got a tie and the significand is odd, then we'll round it up. So I think that's right. I think that's right. I've been writing code for a long time and I haven't run it yet, so I feel like I'm really flying blind here. I mean, it would make me feel a lot better if I was executing this. Why don't I... It's just occurred to me that I could actually write a little test, and even though it's not going to completely execute this, I could at least put some debugging stuff in, or I could have a return value that's got an array with some interesting stuff in. So I think I'm going to do that because it's making me too nervous to not have run this at all. So let's require that. What did I do in the S-expression parser test? Ah, great. Afuk has got some a knowledge bomb. Ties to even is helpful when doing statistics, since for random samples, exactly half of them will round up and the rest will round down, thus keeping the mean the same. That is great. Thank you. Yeah, so that's, I suppose, better than just saying, you know, ties. Because I think what you're taught in primary school is that ties always round up, right? Like, as a kid, you're taught that 1.5 does not round to 1, it rounds to 2. But I guess what you're saying, Afuk, is that if you always round, I guess, away from 0, you break ties by rounding away from 0, then that's going to introduce a sort of statistical bias in that all of your results are going to be the mean of your results is going to be higher, artificially higher than it should be, because that error introduced by the rounding sort of accumulates over all of the data. Whereas I think what you're saying is that given sort of uniformly random numbers, if you round them all to even, half of them will round up on average and half of them will round down, and it sort of cancels out. Yes, okay, you are indicating that I have vaguely understood what you're saying there, so that's good. All right, so thank you for the actual knowledge in place of whatever the hell it was I was offering there. Okay, like looking at this now, I sort of regret. Look at this S-expression parser test. Like, why did I do this instead of just writing a little helper method that could do those assertions? That was very silly of me. So I think I'm gonna... How do I want to do this? I want to have like an assert whatever that does something, and then instead of this, I want to like assert whatever something. So I'm going to have to do this business again where like because I don't want to define that helper at the top, and then at the bottom I'm just going to call mail. My brain is just typing whatever it feels like. So what am I trying to assert here? Well, I thought I would use this as my example. So I've got... Let's take this one step at a time. So my numerator is that large number. My denominator, in this case, is 10 to the power of 15. So this is my sort of high quality, comparatively high quality approximation to pi. I could make this arbitrarily close to the real value of pi, by the way, because, well, RAM permitting, Ruby will let me make this integer as large as I like, and I can make the denominator as large as I like. So I can keep adding more and more digits of pi on here, and I just keep incrementing this number here. But I think this is precise enough for government work. So if I've got the numerator and the denominator, then I want to assert whatever. I suppose. Let's just... what am I expecting? What's the right result here? I guess it's this was what we came up with as being the right answer. Is that... I know that this page, I saw it's got some examples on it. Is pi... Oh, yes. Oh, it's got it as... Is this the same as mine? 0, 1, 1, 0, 1, 0, 0, 1, 4 zeros, bunch of ones, 0, a couple of ones, a 0, a couple of ones. Yes. So although this doesn't have it written in decimal... Maybe it's nicer, actually, to write this in hex, because that's sort of compact. And now that I can see that there's this tempting collection of test cases here, then I'm sort of minded to make it easy for me to rip this off. So let's do this. So this, we believe, is the correct answer. So expected... numerator, denominator. We're going to have to specify how many bits we want. I mean, this is sort of annoying, isn't it? Sorry, I hadn't really thought about, and it really doesn't matter. It really doesn't matter what this looks like. I'm just going to, I know that this isn't good. And there's really no rhyme or reason about like what's a keyword argument and what's a positional argument. I haven't thought this through at all, but I just want to get one thing working here. So let's just do this. Oh, I've done it the wrong. Okay. Just don't think about what you saw there. This is fine. Okay, so this is saying, this is the expected result. The numerator and the denominator are these, and then this is the number of bits. So what does that actually look like? Well, I'm going to call wasmina, well, I guess this is like actual equals wasmina float encode. And what do I pass that? Numerator, denominator, bits. Yeah, so this wasn't too bad, was it? But oh, I don't know. I don't know why I'm saying but. I just haven't thought at all about what I want here. I think this is fine. Raise actual inspect unless actual equals expected. I guess I could be a little bit more expected, got, actual. Let's be slightly more helpful. All right. So now, can I run that? Oh, I'll need to do -i. Ah, great. Why is that happening? Okay, well, see, this is good. I'm glad I'm not saving up all of this pain for later. It's saying significand is nil. Why is that then? So inside this rounding code, I'm immediately suspicious that I've made some kind of typo and spelled significand wrong. That looks okay. Um, I mean, I hope I'm not confused about the scope here of the variable inside that block, but I think maybe I am. Yeah. Oh, it turns out I am. Okay, great. All right. Well, that's fine because I can just do this. This is fine. This is all fine. I could break the significand out here and return, I think, assign it to the loop expression, but that's kind of gross. So let's do it this way instead. Okay, well, that was an annoying... Yeah, I just didn't think that through, but I'm glad I'm executing this. Okay, good. All right. So obviously it hasn't returned the right answer yet, but let's... I just want to do some debugging here. Let's say significand equals numerator divided by denominator. So that's just going to give me some kind of trace of like what is happening when this runs. And I suppose I just charge straight into this without talking about it, that like this is clearly not an efficient way in time or in space to come up with a 24-bit approximation to the number we're being given. In particular, what I'm doing here iteratively by sort of repeatedly doubling either the numerator or the denominator, I'm really just... This is a clumsy way of taking like a log base 2. Like I want to know how many, in order to get this number into this range, how many times would I need to double or halve it? And you can just use logarithms to do that. But the whole reason I'm doing this in the first place is because I got the willies about precision and rounding and funny stuff happening with floats. And so the whole like purpose of the code I'm writing here is just to try and do everything with integers. So this is why I'm taking this approach. This is why I've got this very inefficient loop, which as we can see runs already quite a large number of times. I mean, the way I did it by hand when we encoded pi here was that I just kind of, to call it a binary search would be over-egging it. I just guessed I sort of tried multiplying it by 2 to the 5 and then 2 to the 10 and then 2 to the 20, and I sort of eventually sort of got into this 13 million, which as you can see it has actually found, so that's rather exciting. It's found the same value as me, but this hasn't even guessed it. It's just it's iterated its way there by doubling and then doubling and then doubling again. Not very efficient, but you know, as I said way back when, I'm much more interested in, you know, correctness than I am in fastness. You can't even read that, but you know, I want to get it right, and this feels like the way to get it right, even if it's not particularly efficient. Okay, so that's very encouraging. That loop is running as I was expecting, and it's found the answer that I was expecting. So I'll comment that out for now. I remember we did actually have to round this. The remainder is blah, which is larger than half, so we need to round up. So let's see. Rounded. I thought I was going to interpolate something in that string, but then I didn't. Okay, yes, we are rounding. So that's good. So far, everything is proceeding according to my design. Okay, adjust the exponent to account for scaling. So what I mean by that is that in the final encoded float, we're going to provide an exponent, which is what do you multiply? We're going to multiply the significand by 2 to the power of something, the exponent, in order to get the actual number that we're representing here, the floating point number. Now, every time I have got I've doubled, in this case, I've made it larger, right? So I'm making the numerator larger, which then has the knock-on effect of making the significand larger. So that's nudging it into the range of acceptable significands. I need to remember that I've done that and compensate for it in the exponent. So every time I double the significand, I need to reduce the exponent. So if we start, I mean, I guess this is what I'm saying actually. If we start with, we're going to be multiplying by 2 to the power of 0, which is just 1. Then what I'm saying here is that every time I double the numerator, I'm going to reduce the exponent by 1. So that initially is going to make it 2 to the minus 1, which is half. So that means that when we multiply by 2 to the power of minus 1, that's going to cancel out the doubling that I did here. And likewise, when I double the denominator and make the number artificially small to get it in range, I need to cancel that out by incrementing the exponent by 1. So the place where I put this comment isn't really appropriate. It sort of needs to go up here. Scale the significand up, down until it's in range, and adjust the exponent to account for scaling, basically. So we're going to do that as part of a single operation. So let's see at this stage, what's the exponent? I'm not sure what I want it to be, actually. But I did write some stuff here about saying it's 2 to the 22 times too large. So I think what I'm expecting to see here is minus 22. Oh, in fact, why don't I just add the exponent to I've already got this here. Let's just say that this is 2 to the power of exponent. So this is like scaled 2 to the power of exponent, I guess. Right. Oh, well, it's not, that's the, must be scaled. It's not what it has been scaled, it's what it needs to be scaled. Yes. So this number, 1317694, I'm just going to make that a float for the purposes of illustration here. So if I multiply that by 2 to the power of minus 22, I will recover pi, right? So that's what this is saying, is like these are the two essential results of this process. I get this integer that is a whole number that is crucially it's the right size. It's exactly 24 digits long, binary digit. So it's the right size to be expressed inside a 32-bit float. And I've also kept track of what do I need to multiply this by 2 to the power of in order to recover, in this case, pi. So I'm amazed that this is going so well. That's exactly what I wanted to happen. Okay. Round the significand if necessary. We've dealt with that. Adjust the exponent to account for normalized significand format. Right. So what I'm talking about there is that, yes, because this is our 24-bit number, but when we put those 24 bits into the flow, it actually represents this normalized representation, which means there's a leading one, and then there's a decimal point, a radix point, and then all of the rest of the digits sort of come after the decimal point. So this is, however many digits we have here, this is that many powers of 2 smaller than the number without the dot in it. So this is saying it's 2 to the 23 times smaller, because this part here, the fraction, is 23 bits. So I think actually what I'm going to do is, having computed the significand bits, I can just say fraction bits is 1 less than that. Because like I said, the top bit of the significand is not actually stored, and it's the only bit. It gets treated differently, it comes before the decimal point, and all of the rest of them are going to be after it. I'm just going to say decimal point. I know that it's not, but That's what everyone calls it, isn't it? Decimal point. So what this means is that I need to adjust the exponent, because when I write this in, it's going to represent not the number that I wanted, but a number that is 2 to the power of 23 times smaller than I meant. So does that mean I need to add? I'm not very good at the mental arithmetic of this, but I think it does. So I'm just pausing there because I've had an idea, but let's see this work, and then it's not a very interesting idea. But I think this is right. I think if we add, so this is going to serve to scale up the number much more than we'd previously asked for. So previously we're asking for it to be, for it to be scaled down, by 2 to the 22 times. And this is going to say, well, also we want it to be scaled up by 2 to the 23 times, because the way that it's been represented has made it 2 to the 23 times smaller than the 24-bit integer that we were hoping to express here. So this almost entirely cancels out the work we've just done. So I'm expecting this to be 1, I think. Yeah. For pi, at least. The idea that I had is that instead of adding this on here, we could just initialize the exponent to be. So I think I'm gonna just do that, actually, because I think that makes more sense. So rather than initializing it to this sort of arbitrary value of 0 and then adjusting it later, I think I'm gonna say, initialize the exponent to account for normalized significand format. So it's going to start out being, in this case, whatever number we write, we want it to be what we meant was a number that's 2 to the 23 times larger than that. And then this loop is going to adjust that up and down relatively, depending on how many times we double or halve the number that we're trying to express here. But it's going to start from this baseline of being 2 to the 23 times larger than what we say, because the encoding makes it 2 to the 23 times smaller, and that just cancels it out. All right, add bias to exponent. Yeah, I like I said, I talked about this in some detail yesterday, so I'm not going to repeat myself. So what I want to write here, so this is another sort of slightly annoying situation, is that I want to be able to say, I want to be able to calculate the bias, which is, so in the case of this float format, the bias is, it's like all the ones here with a 0 at the top. So I want it to be this, 0, 1, 1, 1, 1, 1, 1, 1. And the way that I calculate that is that I do 1 shifted left by exponent bits minus 1, and then subtract 1 from that whole thing. So shifting the 1 up 7 places, we'll put a 1 in this top column, and then subtracting 1 will sort of underflow, and then all of the other bits will become 1s. But is exponent bits a thing? I don't understand how it... I don't understand how it. I'm really confused about how it completed that because I don't have exponent bits yet. That was the. Oh, maybe it was exponent bias because it's only one character different. Maybe I misread it. Anyway, whatever happened there. Yeah, I don't have exponent bits, but if I did, I could do this, and then I could say exponent, just add the exponent bias to it. I think if I run this, it's going to say, I don't know what exponent bits is, so I need to add this to this thing. In fact, I'm going to put it before. Oh, did it pick it up from... Oh, yeah, okay. All right, fine. That's where it got it from, because I've already got it in that file. All right, good. I'm glad I'm not completely losing my mind. So 8 bits of exponent, 24 bits of significand. Let me just substantiate that. Yeah, there we go. 1 sign bit, 8 exponent bits, 24 bits of significand, 23 of which are actually stored. So, and I suppose I'm going to move the bias up here as well. Like, I feel like what I'm doing here is taking this number 32 and then like massaging it into a bunch of other numbers that are part of the specific float format. That's why I'm trying to put all these together, is like, this is the part where I'm going to figure out what all of the parameters of this format are. And just saying that makes it incredibly tempting to extract this into like a float format or a precision or something class that can wrap all of these, because these are quite fiddly calculations. It would be nice to just have all of this, just tie a bow around it and say that is the object that represents single precision or whatever, but I'm not going to do that. A folks asking, do you really need to declare exponent bits and significand bits separately? I suppose not, because I could just subtract it from bits, couldn't I? If I know that there's a single sign bit. Yeah, that's what you're saying. If sign bit is always 1, then 1 can be derived from the other. Yeah. Yeah, I think you're right. So yes, I don't really need to put it here explicitly. I'm having an internal debate with myself about sort of concision versus clarity, I suppose. Like, there's something to be said for having it written out like this, but because when you look at, when you look at a table like this, it's always got like, 8 bits of exponent and 24 bits of significand. So there's something to be said for having those written out, even though obviously these are not independent variables. I'm going to add that to my, let's say, just compute exponent bits from significand bits, or vice versa. I'll go back to that when I've actually got this working. For now, I'm just trying to not do anything clever because I'm already right on the edge of my competence at this point. So I don't want to jinx it. Okay, so now I think, that's slightly worryingly, I'm sort of at the end here. As I've been doing this, I've had a variety of unpleasant thoughts about. I'm just going to write a to-do here. What about subnormals? What about 0? What about infinity? And actually, I've just had another thought. What about sine? So there's actually lots of details that I haven't covered here, but that's fine because I'm sort of trying to. I'm studying to the test, right? I'm trying to get this test, which is the completely vanilla, but also the most common. Oh yeah, nans. Well, Yeah, Folk is asking about not a number. So fundamentally, this function is not for encoding nans, it's for encoding numbers, right? This is when you've got a rational and you want to express it as a float. So that's a really good point, because surely there's going to be, before too long, some nans cropping up in here, and I'm going to have to deal with them. In promote. But yeah, I mean, you know, at some point I am going to have to deal with those, right? So I would say that, you know, this is a bit of an unconvincing thing for me to say, but I think nans are sort of out of scope for this function that I'm writing, but I'm clearly going to need to support them in some way. And especially if I try to replace all of the existing floating point manipulation I've got in my code wholesale, basically stop using pack and unpack and just call into this code, I'm going to need another version of this for encoding nan. So I'm either going to have to do that by having another method, because for a nan you don't provide a numerator and denominator, you provide a payload and a width. You know, so something like this, payload bits. So I'm either going to have to define another method to do that, or I could do it with polymorphism, right? Like have a nan and a finite class. And actually there's another one here, encode infinite, which is just, oh, and yeah, this needs to know whether it's negated or not, and actually so does this. And actually so does this, like that's the sign that I just talked about. So I might need to, yeah, I'm sort of, for infinities and not a number, I am going to have to implement those differently. There's a little bit of subtlety around infinity because, well, I just haven't thought about this at all yet. But if it's not, I haven't thought at all about what the valid exponents are. I've thought about the valid significans here, but this loop at the moment allows the exponent to get arbitrarily large or arbitrarily small, but that's actually not correct, because the exponent has to fit inside 8 bits or inside 11 bits, depending on the float format. So if this loop runs out of wiggle room in the exponent on the upper end, then we're going to need to encode infinity, or positive or negative infinity. But that's a property of the width that you pass in here. So I think there's sort of two different things going on here, where we're going to need something that allows you to just say, I just want an infinite number, please. Or I want negative infinity. But then there's a slightly more subtle thing here, where actually encoding, depending on the precision, encoding a completely valid rational number might also give you a positive or negative infinity. So I definitely need to deal with 0 and subnormals here. I think I need to deal with infinity as well. I mean, basically all of these are about extremities of the exponent. You know, if the exponent gets too large or if it gets too small, then I need to worry about this here, but I just haven't thought about that yet. So and yeah, the sign is going to be a problem. For now, let's say the sign bit is equal to 0. Pass this in, probably. Okay, so assemble bits into float. So what I need to do is I've got the sign bit. So there's a choice of ways of doing this, right? Like I've got Oh, in fact, before I start talking about assembling the bits that the parts that I need are, I need the sine bit, and I need the fraction, and I need the exponent. Let's just call this sine, I suppose, because all the rest of them are just called, no. And I've just hard-coded the sine bit to be 0. I'm going to need to pass that in. I know the exponent. The fraction, though, is the significand with the top bit chopped off, right? I really don't like this bit suffix because so far I'm using underscore bit to like talk about how many bits, and I think this is going to confuse me, so I'm just going to make this sine. So the sine, the exponent, the fraction. The fraction is, we take the significand and then we mask it with, I think this is right, 1 shifted left fraction bits minus 1. So again, making the number that's 1 larger than the largest possible fraction, and then knocking 1 off to flip all of the, in this case, 23 bits to be 1. And then we use bitwise and to just sort of mask out all of those bits. So, so I think I've got all the pieces I need now. So now what I need to do is assemble this 32-bit number where the sine bit is at the top in bit 31, and then bits 30 through mumble, because I feel like I'm going to do a off by 1 error here. 23, yes, are the exponent, and then bits 22 through 0 are the fraction. There are a couple of ways of writing this code. I think the way that I like to do it is to say, I'm going to take the sine. Basically, what we want to do is combine the sine and the exponent, right? But the problem is that the sine is, the exponent is going to splat on top of the sine. So what we have to do is shift the sine exponent bits to the left. So this is going to give me the sine and the exponent sort of concatenated, essentially. And then I can just repeat this and say, well, now that I've got that, I want to concatenate that with the fraction. But then I've got the same problem, right? That's just going to splat on top of what I've just computed, unless I shift this out of the way first. So I kind of like this like sine, and then it's almost like you're sort of concatenating on the exponent, and then you're concatenating on the fraction. The question is that too clever for its own good? I don't know. The problem is there's not really a nice way of writing this. I suppose the nicest thing to do would be to have a little helper method that just sort of does a fold left, sort of does an inject over, that knows how to concatenate multiple n-bit numbers together where n is different for each number, and you just pass in, here are the numbers, here are the widths, splat them together. But given that we only need it in this specific case, I think I rather like the regularity of this idiom, so I'm just gonna do it. Right, so I mean, I guess I can actually run this test now. Oh my golly gosh, it's worked. Okay, so the fact that there's no output there means that is actually working. Wow, I was not expecting that. Okay. Let's call this assert float encoding. So that's rather good. What do I want to commit here? I think, like, obviously I need to pass the sign in. Let's do this. Negated. And then this would say negated 1 or 0. And then the test is going to fail because I'm not passing that in. So I'll make this default to false so that in the cases where we don't care, we don't have to provide that. Well, I do need to pass it in, don't I? Okay, great. I'm just trying to get this to a point where I feel like I could actually commit it. I'm going to take the to-dos out for now. And the puts, because they're just for me. Okay, so I mean, this isn't hooked up to anything yet, but for now I'll just say start implementing float encoding in Wasmina float. This isn't hooked up to anything yet, but the intention is to get it working well enough to be able to implement, what was it we were implementing? Convert i64s with it. F64. Hold on, I've forgotten what the, sorry. Oh, that's not what I want. Conversions. Oh shit, it is actually calling that. Sorry, I'm getting in a mess here. I think it was F64 convert i64s. So those to-dos I removed, I'll just summarize here. I haven't yet thought about, what was it I haven't yet thought about? Nans, infinities, subnormal numbers. Yeah, that's it. But we'll need them all eventually. Okay, so, well, I noticed that this is trying to call into it, but it's not API compatible because I have to say negated. Well, actually what I need to do, I could have just passed in, well, I am passing in a signed integer here. I could have detected the sign of this inside encode, but I think it's a bit annoying because if if you try to detect the signedness of the number, then you get into the situation where you're sort of, you need to account for the fact when both the numerator and the denominator are negative, and you get a positive quotient. And I would just rather, I'm sure it's not difficult, but I just don't want to think about it. So let's say we're going to pass in the absolute value of this signed integer, and then here we're going to ask whether the original integer was negative. Right. So actually, I'm just going to stash this and rerun that test so that I can remind myself of. So yeah, it was plowing through a bunch of these convert i64s, but then it was this one where it was expecting 159385519, which I think is this last one. And it got one off. So I seriously doubt this is going to work, but let's just run it anyway and see what happens. I think this is worse because I think we stopped here. So yeah, it's the third i32, and this doesn't surprise me because this is exactly why I put this comment here about zeros, because there's this loop will never terminate if the numerator is 0, because no matter how many times you double it to try and make it fall into this range of significans, 0 is never going to get large enough to fall into that range. So I think if I put this back, what I'm going to see is essentially an infinite loop. Yeah, and it's desperately trying to make it larger and larger and larger to try and push it up into that range. Oh, F32 i64. Oh, so are you saying that it's Afuk, are you saying that something good has happened? Have we gone past the place that it was failing? You're right. F32 convert i64s. So, oh no, I think maybe it's getting stuck here. So we actually still don't know whether this works, but we're stuck on this one. I'm sort of tempted to. Okay, I'm all over the place right here, but I'm sort of tempted to make a unit test for this one that we know is failing, so that I can at least discover whether, because the whole point of this is to have different rounding behavior than Ruby, and if this code just gives the same answer as Ruby is doing, that's not necessarily the end of the world, but it would be pretty annoying. So I think before I get into that zero situation, which I think it's fairly obvious what's going on there, let's just try and make a unit test that recreates this situation. So I think this is right. F32 convert i64s. It's all of these. So I better fix that commit message, hadn't I? Because that was a lie. But yes, I think it's this F32 convert i64s, and I think we determined it was this one that was going wrong. So can I maybe I can confirm this? So if I say, let's take this 64-bit integer, it's just a normal integer, and then we convert it to a 32-bit float. So I pack it as F, and then I unpack it as a F. That's not very convincing, is it? F32 convert i64s expected this got that. So what's the code doing? Right. Oh, yes. Okay. Hi, Zeta. Sure, I could just. Well, the problem is it's off by a whole one, right? But yes, I mean, I could have an extremely generous assertion here that allows two integers to be one different and still be considered to be equal. I suspect that I would live to regret that. So I think I'll for now I'm going to plow on with this and see how far I can get. I realized that I was doing the wrong thing. This should not be packed as a float. It should be to floated. And then that gets, well, I mean, I guess that's sort of what I was doing anyway. Pack that as a float. Unpack that as a long. And this was saying it was expecting to get this. And instead it got that. Well, what does this look like then? Yeah, I mean, I suppose this is the problem. It's treating these two as being the same value. So, Foki, you're saying that this is the last passing test that I had. It's this one is the problematic one. I need to be way more disciplined about this than I'm being at the moment. Okay, after the zeros, there's 1, 2, 3, 4, 5, 6, 7 passing tests. 1, 2, 3, 4, 5, 6, 7. Right, okay, so it's not... yeah, you're right. I was looking at the wrong one. It's this one. Okay, fine. Oh, this is in hex format, so I'm just going to abandon hope at this point. But so this is saying if I take this big integer, convert it to a float, pack it as a single precision float, and then unpack it as a long, then I get this number. Right. But I should get this number. So something is going wrong here. So I'm going to endeavor to make this into a test, I suppose. Because I know what the big one is. So assert float encoding. This is the... That's the big number that I want to represent as a float. That's not right, is it? There's something here that's the right answer. And the test is saying that it's expecting this to be the right answer. Can I express this any more? Yeah, okay, that looks a little bit less arbitrary. So it should look like this. The denominator in this case is just 1 because this is literally the number that I want to represent. And I want it to be a 32-bit number. So I think that's right. Ah, okay. Well, that's passing. So that's good. So that means that my implementation does agree with what WebAssembly is expecting. So, so that gives me some hope that once I get past the 0 issue, then the strategy of using my float implementation here is actually likely to be successful. So add test for encoding. But Afuk, wasn't it getting stuck here? I thought it was getting stuck on this 0. You're suggesting it was getting stuck on this 0. I mean, I might be wrong. Maybe I was just assuming that it was getting stuck on this one, but let's see. Add test for encoding. As a float. Okay. Well, I will believe you then. Oh, let me take that out. Take that debugging code out for a sec. Okay, so how far does it get? So it's right at the beginning of any of these convert functions. F32 convert I32S. I'm a little bit confused about where this is. It this one? I'm a little bit confused about what's going on there. Yeah, I agree, Chris. It should print line numbers, or it should print something to, because the thing is that, well, no, I don't have any excuse for this. I think previously seeing the name of the function being invoked in the test was sort of enough. But now there's so many invocations of the same thing that I'm really just losing track of. I'm going to add that to my to-do list. Let's see. So this was Afuk's idea. Add line numbers to assertion output. So yes, I think we're agreed that we actually hadn't seen this pass before, but now we have a reason to believe that it eventually will. But see, previously I thought we were getting stuck on this one. Now this output is making me think that maybe we're getting stuck on this one, and I'm not quite sure why. But let's dig into it. Wow, why is that? How does it go that fast? Okay, well, that's no good, is it? I'm pretty confused about what's happening here, to be honest. I don't understand why it's getting stuck on that. Let me just print this out. Numerator 1, denominator 1. Like, it looks like it's running these ones. Am I just looking in the wrong part of the file? Yes. Okay. All right, fine. Mystery solved. I was just looking in the wrong part of the file. Thank you, Chris. I should have had line numbers. You were absolutely right. I was in completely the wrong place. Okay. All right. The world now makes sense in some limited way. So the problem is this 0. I'm going to make a unit test for this. So what's this saying? It's saying that well, I think I'm right that the representation of 0 is just 0. I think if you take 0 and you pack that as a 32-bit number and then you unpack that as a float, you get 0.0. So that's the correct encoding, is all zeros. And what we're being given here is a numerator of 0, denominator of 1, and 32-bit. So this is the unit test that will provoke the problem we're having. Yeah, which is that it just gets stuck in an infinite loop. So really the issue here is that all of this guff about, well, I would say all of this code and all of this code doesn't make sense for zeros. And furthermore, I would say that this doesn't make sense for zeros. So I would say that all of this needs to be conditional on knowing, you know, if numerator is 0, do something sensible. Else, do all of this stuff, I think. The reason why the exponent doesn't make sense is that the reason why we were setting this to be the number of fraction bits in the first place is because we cared about the interpretation of that number. I mean, in reality, if the fraction is all 0, or if the exponent is 0, it really doesn't... Okay, hold on, let me think about this. I was going to say that it doesn't matter what the exponent is, but the way that you communicate as 0 is by setting the exponent to be 0. So do I just want the significand to be 0 here? Is that it? Is that what doing something sensible consists of? And then we... Oh, we don't want to add the bias to it either. Like, we just want all those bits to be zeros. So all of this stuff about rounding the significand and biasing the exponent and all of that is on the assumption that you're not trying to express as 0. So I think I'm just going to go with... And by the way, you know, the reason I'm using the numerator as a proxy here is that that's... do I mean what I'm about to say? What I was going to say was that's the only way you can get a 0 here, but that's not really true, is it? If you have a, you know, a small enough numerator and a large enough denominator, then you do get a 0. Okay, look, I'm just going to go with this for now, and then we're going to think later about, or see if it becomes a problem. Yeah, my brain hurts trying to think about that. Okay, well, that works. That gives the right answer. So effectively, we're just skipping all of this logic about finding the right exponent and the right significand and stuff. We're just saying, well, if it's supposed to be a 0, then all of that stuff is 0. We are... It might be that this is a temporary problem, actually, because I'm just going to write this in here. Remove special logic about 0 numerator if possible once subnormals are implemented. So subnormals are very small numbers, and I'm thinking whatever code we put in here to handle very small numbers. So we don't necessarily have to, what I'm thinking is the more general solution here might be not just to spot 0 numerators, but actually allow this loop to run to exhaustion, to run to the, to the smallest possible exponent, and it's still not able to make the number large enough to get it into range. And then that's going to like trigger some other logic that we have to handle subnormals. And really, I think the 0 logic should go there, because we want to get a 0 not only when the numerator is literally 0, but when the quotient of those two things and the remainder after division is sufficiently small that it's so close to 0 that the nearest float that can represent it is 0. And at the moment, I'm sort of ignoring that case. But that's fine. For now. Because it makes that test pass. And if I run conversions... Oh, it doesn't get us very much further. It gets us one more further. Okay, but that's progress. So let's make a commit. I think it's, well, where are we at with this? Like, is it reasonable for me to plug this in? I mean, I guess so. I mean, it's not really any better. In fact, it's worse than what I had before, but this is what I'm working on. So why don't I add this? So let's say use wasminer float encode in. Well, let's just say this isn't working any. This isn't working much better than Ruby's built-in approach yet, but at least we're improving it. Okay. So yeah, I was gonna add this additional test, and then let's just take this to do out. Okay. Support 0 numerators correctly in wasminer float encode. And I'll just add a note here to say this isn't entirely sufficient because we also need to support rounding very small numbers down to 0. But it's enough to get at least one of the tests passing for now. Oh, I also didn't want the puts in there. Okay, yeah, I'm trying to keep the content of these commits relatively clean, even as I'm making a big mess here, actually in the code. Okay, so this one failed. Now, what is this trying to do? So we got the... Oh, hold on. This is... F32 convert I32S. So yes, okay, that's 1.0, that's -1, that's 0. This number here, what is that supposed to be? Okay, so that's a 31, that's the largest 31-bit integer. And apparently that can almost exactly be represented as a float, but not quite. Where are we going wrong? Supposed to be 13254. Let's just see that. So if I pack that as long and then unpack that as a float, right, that's the right number, 2147 blah 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 648. So that's what we're supposed to get, but instead we're getting this, which looks completely different. Ugh. So what do these numbers look like? If I print this as a 32-bit number, so this is what we're supposed to be getting. So I mean, that's some exponent and then all zeros in the fraction, and there's an implicit 1 in the significand. But instead we're getting this, which looks worryingly different. Oh, the exponent's wrong. Okay. Well, let's make a unit test. I think this is a rounding problem. But let's do this and then we can diagnose it. So it's supposed to be encoded as this. Learn to type. And the number that's being represented is this one, which I think is probably also more sensible as hex. Yeah. And it's just, that's an integer. Excuse me. All right. So we're expecting that unit test to fail. Yes. So that's the same expected 132540064 got 131. Okay, so that is just wrong, but it's wrong in a specific way, which is that the exponent is 1 smaller than it should be. Now, my suspicion of what's happened here, looking at the available information, is that it's got rounded up in a way that that should be reflected in the exponent, but we don't have any mechanism for doing that at the moment. Like when we round it, we just increment that fraction. So I suppose this is my hypothesis, is that before rounding, all of this fraction was ones, and then to round it, we've incremented it by 1, and it's flipped all of these bits to being 0. But now that's made the number 25 instead of 24 binary digits. And so we need to... Is what I'm saying making sense? It feels like that's gone in the wrong direction. Oh, yeah. Yeah, I'm not quite sure what I'm saying. Yeah, that makes sense. Yeah. The number has become larger, so what we need to do is make it smaller again and then compensate for having made it smaller by incrementing the exponent. So that step that we do inside the loop to sort of steer the significand into the Goldilocks zone between the minimum and maximum significand so that it's a 24-bit number, we need to do that again after rounding, because rounding might, if it was right at the boundary of the Goldilocks zone, rounding it up might bump it outside of the Goldilocks zone, in which case we need to pull it back in again. So we don't really need a loop. Well, why don't I... That was all speculation. Let's do some debugging. So let's say rounding. And then once we've done the rounding, I'll print all this out again. So let's see if that is indeed what's going on. So the significand becomes this. Yeah. I mean, well, not to toot my own horn, but this is exactly what I said. So these are all ones. Then this gets incremented by rounding. I mean, clearly this test has been designed to provoke this very problem, right? It gets incremented by rounding, and now it's become a 25-bit number, but we're still only just using the bottom 23 bits of it, because we thought that the 24th bit was a 1. So this is all wrong. We need to adjust the exponent. I mean, I'm sort of relieved that that problem is sort of amenable to understanding by a human. I'm just trying to think, like, what's the right way to fix it? I mean, I know how I want to fix it, which is just to copy and paste this loop in here. And therefore, that is what I'm going to do. It's not really necessary, because I actually just need to... I only need one iteration. I only really need this bit. But then again, if I pull this loop out as a helper method, then it means just another call to the helper method here. Doing one iteration of a loop and then breaking is not the end of the world, but obviously the code duplication there is not very desirable. But in any case, let's see if that actually fixes it. No, it doesn't. Damn. Why didn't that fix it? Oh, because... because this loop body immediately overwrites the significand, and the body of the loop only adjusts the numerator and the denominator. So I need to I need to be a bit less stupid about what it is that I'm doing here. I think what I want to do is sort of reset what... Okay, bear with me here. I know this is over engineering because I don't really need this whole loop here, but my mental model of this is that I've now got a new rational number that is the approximation I want to use, and that rational number is this thing. This number is an integer. So what I want is to say the numerator is this significand, which I've just computed a new value for, and I guess the denominator is just 1. So I'm sort of, I mean, actually, I could just recursively call encode at this point. Like, really what I want to do is encode a different rational that has already been rounded so that it won't need any more rounding. So this is sort of, I could recursively call this function at this point, or I could just glue in this scaling loop to do one. So yeah, now the fact that this immediately splats over the significand. Yeah, you're right, Afuk. I really only need this bit of code. But I suppose the reason I'm doing what I'm doing is that I'm trying to get my head around what conceptually is going on here, which is that I've already implemented this operation that is the sort of general version of nudge a rational number into the Goldilocks zone and also plop out an exponent. And that's exactly that's in general the operation that I want to do here. I mean, you're absolutely right that the significand is never going to be smaller than the minimum. I'm always just going to want to do this test. I think I'm driving towards extracting this thing, right? And then I think it's meaningful to call, if I have this extracted, I think it's meaningful to say, I want to do this operation again. You know, the problem is I've nudged it. I might have nudged it out of the Goldilocks zone. And so I want to pull it back in. And that's what this loop does. But yeah, it's a bit of a sledgehammer to crack a nut, given that all I need to do is just check this and, yeah, if it's gone out of range, then I guess I just need to halve it and increase the exponent. Is that right? Yes. Anyway, I'm going to run the test and see what happens. Okay, that does work. Golly gosh. Okay, so I'm going to justify where am I at? This is all becoming a bit of a mess. So what I'm going to do is, rather than this copy paste business, so if it's saying, instead of breaking in your initial loop, you can also do your rounding checks and update numerator and denominator and loop again. Oh, so like do the rounding check in here. The problem is, I don't think that's right, because I don't think that rounding it's not going to commute with the other operations I'm doing here. Like, when you round, you're throwing away information, right? And so I think my instinct is that it's important to wait until the very end and do rounding only once. I think if we were to, I understand the point that you're making, which is that we could try to insert it into the loop here. But I think if we do rounding, I don't think we know whether we need to round until we've got our 24-bit number, basically. That's my gut feeling. And if we... I'm not 100% sure about that. I'm going to write it down. Can we do rounding inside the scaling loop instead of once afterwards? Okay, what was I going to do? What I was going to do was extract this so that I can call it. So I wanted to pull out all of this code. I don't know what to call that. And I don't know what... Oh, hey, Daryl, thank you. It's very kind of you to say. I'm glad that you're enjoying this. I mean, I think today's episode is all over the place, but I'm glad you're finding it educational or entertaining. Okay, so I've got this function foo. Oh, I appear to have lost the contents of my... Let's do that again. Okay. That is going to be foo. Let's paste it. I should really be better. I should really be better at everything. Okay, so foo, let's make foo private. Scales the significand up and down until it's in range. That's obviously not going to work. What does foo need? This is my extract method refactoring, is that I just pull out a method with no parameters and then chase all of these errors. Undefined local variable on method foo. Well, that's not what I was expecting. Why has that happened? Did I not put it in the module? Does private somehow prevent that from being a... Oh, I guess so. Okay. Undefined local variable or method numerator. Yes, you make a compelling point. We definitely need to pass that into foo. Likewise, denominator. What else do you need? Oh, you need the minimum and maximum significand. That's annoying. And you need to modify the exponent. So we'll just pass that by reference. Not really, of course. We're going to need to return that. That's how Ruby works. What the why is that passing? That's not right. This function doesn't return anything. That test shouldn't be passing. Oh, unless that... Yeah, okay. I mean, unfortunately, that does somewhat support the Fuchs hypothesis about rounding. But so what do we actually... What's the point of this foo method? It's to adjust the numerator, the denominator, and the exponent. So once this loop has finished, we need to return numerator, denominator, exponent. And then we assign those here. So now I think the test is going to pass. Yes. in case it's not clear, what I'm trying to do here is extract this method so that I can call it down here. So what does this thing do? This is why I kept this comment, so I can remember what it's supposed to do. Scale the significand up and down. Let's just call it scale significand then. And the fact that we don't actually get the significand, I think, is fine. And do we actually need the numerator and the denominator at this point? Sort of. Like, I'm thinking, could I just return the significand and the remainder instead? But you do need to know the magnitude of the denominator to be able to make this rounding decision. Potentially, this rounding logic could go inside scale significand, and then it would just have to call itself recursively to when these get adjusted. But anyway, the point of extracting that method was so that instead of pasting that loop in there, I can just do this. I'm just thinking, now I need to do this again. Yes. It's a bit of a mess, isn't it? So I don't really need that. And in fact, I don't really need that. Although, I guess that's nice. This is a little bit messy. I think I'm okay with it though. And I think I'm happy to, well, maybe I'll leave that comment in for now, but it's starting to feel a bit messy and redundant. I think if I leave this out, why is that not failing the test? I suppose it's actually only the adjustment to the exponent that we care about at this point, but I feel like if the numerator and the denominator have changed, then you really need to recompute the significand. Yeah, I think you're right, Ufuk. It doesn't really matter. So anyway, sorry, this has all gone a bit horrible. What I was trying to do here was extract this method so that I can use it. So extract scale significand method for reuse after rounding. And then the next commit is going to be reuse scale significand method after rounding. So what I'm going to say here is if the significand is already at its maximum value and rounding increases it by 1, we need to rescale it into the appropriate range. Now that we've extracted scale significand, that's just a question of calling, it's just a question of calling that method. So like I say, I sort of acknowledge that this is a bit of a sledgehammer to crack a nut, but I think conceptually I would rather reuse an overly general operation, which only a small part of which is actually required in this case, than implement something different and then need to understand that that actually is doing the same thing as the more general operation, but it's a special case of it. So I think I prefer it this way around. And yeah, you're right, Afuk, that it didn't matter that I wasn't recomputing the significand because we only ever get the trailing zeros of the significand anyway. So this is what recomputing it here is doing, I think, is turning it from a 25-bit number where only the top bit is set into a 24-bit number where only the top bit is set. But given that the fraction is only the lower 23 bits of the number, those are indistinguishable from an encoding point of view. But I think that conceptually, again, I think it is the significand that we meant is this one, the one that we're recomputing, the ratio between the numerator and the denominator as an integer. I mean, it feels like there are several hidden concepts inside here, which I am keen to extract through refactoring. But for right now, I'm sort of happy that this is just working. So let's add a test. What have I previously been saying here? Add test for encoding this thing as a float. This was previously triggering the bug of rounding a significand out of the, above the acceptable maximum. Exactly, Afuk. The significand's value is, to me, deeply significant. Right. Now what? What are we doing? So this is feeling a little bit more like the sort of double loop TDD that I'm used to. This is really the first opportunity I've had to actually get stuck into it because I'm kind of bouncing off of the acceptance test and then writing a unit test and making it pass, and then we're going back to the acceptance test. So this is finally giving me the experience that I was looking for. Okay, that's good. So we passed that chunk of F32 convert I32 tests. I think we're now further into the convert I64S, the F32 convert I64S tests, which again, as I'm sure Zeta is thinking to himself, if I had line numbers, I would know exactly which one we have stumbled upon here. Oh, hold on. This is me raising an exception. Line 250. I thought it was a test failure, but it wasn't. It's this guard. So it's, oh, it must be here. So up until now, we've had this guard here that said that we only support F32 dot convert I32S, convert I64S. And the reason I had this here was because I'd hard-coded the format strings that we were using to encode the integer as a float using pack and unpack. But now, well, we're going to get an exception in a different place. But I think if I remove that, now we're going to get a complaint that we've passed 64 in as the width of the float to encode, but right now my comprehensive float formatatron 5000 here does not know about 64-bit floats, but I think we can fix that. So in a 64-bit float, it's an 11-bit exponent, and I want to say 53-bit. I always get these off by one. Oh no, I didn't get it off by one. Okay, 53-bit significand and a 52-bit fraction, but you know, that is what this means. So in a just world, that would be enough to make that test pass. I mean, I haven't written a unit test for it. Oh my golly. Okay, great. Wow. Okay, so all of those convert I64S tests passed. This is a pattern match failure because we haven't implemented convert I32U. Wow. Okay. So let's I am going to write a unit test, I'm sorry. The reason is what is the reason? Oh, just so that I can make a commit that's just adding that 64. Like what I want to add is just this. Without touching the interpreter yet. I just want to add 64-bit support to this method. So let's add a unit test for this method that confirms that such a thing works. So what's the test saying? I mean, I think I can probably get away with doing this. So this is saying what is being encoded is 1, the 32-bit 1. Although, of course, this method doesn't care how many bits this is. But, you know, this is a 32-bit 1, just so you know. And then we want to encode that as a 64-bit. Just realized I don't have any unit tests about negative numbers, but those have all just worked. So, and all it is just changing a single bit. So I guess that's wasn't interesting enough for me to write any unit tests for it. So what is the expected value here? Whatever this is as a 64. I'm pretty confident that I can trust what Ruby thinks 1.0 is. If I pack that as a double and then unpack that as a quite long integer, let's see that as hex. Okay, fine. All right. What? Oh, that's because 0 is not the correct. 0 is not the correct denominator. I was just checking to see if anyone was paying attention. No one complained about that 0. There we go. So I can use that to justify. So add 64-bit support to Wasmina float encode. Right, and now say support F64 convert I32S and F64 convert I64S instructions. So let's just briefly explain. This was previously limited to 32-bit floats because of the hard-coded pack format strings, but now that Wasmina float encode knows how to encode 64-bit floats, we can just pass through the appropriate number of bits directly. Great. Cool. How are we doing for time? It's only 10:30. Okay. I was going to say I was quietly optimistic. I'm not really, but we're definitely making progress. I'm quietly optimistic that progress is being made here. Something that I was originally hoping I would not have to implement. It's kind of going okay. This code does seem to be working so far. Still haven't thought about subnormals in Infinity, so that's giving me the willy slightly. But let's see how far we can get. So it's complaining about I32U. So I think probably that we're going to need I32U and I64U. And I think that this is just going to be like, these are the unsigned, this is using the unsigned interpretation of the integer argument. I don't think I even need the integer bits. I think it's just that. That's my theory. All of this business and the taking the absolute value and checking to see whether it's negative is because we're using the signed interpretation of the integer argument. If we're using the unsigned interpretation, then it can't be negative, and it's equal to its absolute value, and we don't need to know how many bits wide it is because we're not converting it. So I think that should just work. I32U. They all passed. Wow. Okay. I mean, that feels pretty good that just worked. So I guess this is implement the something instructions. I quite often do this where when I go into the amend view, I can actually see what I've implemented. It's this. These are like F star dot, because we just support whatever width you want. As long as it's 32 or 64, you can have any width of float you like. Satisfyingly, this is just a single call to Wasmina float encode. Not really adding any information there apart from that I was smug when I made that commit. Okay, so now promote F32. Is that the first one? Okay. What is that? What do we think it is? Well, it certainly looks like what it's doing is taking a 32-bit float and re-expressing it as a 64-bit float. Okay, the reason I'm sighing and pausing is because by the time we get this float, it is going to be an integer, a 32-bit integer that represents a float. And to reinterpret as a 64-bit integer, what we need to do is the opposite of the operation we've already implemented, which is to decode. Instead of turning a numerator and a denominator and a bit width, and whether it's negative or not, into an integer, we want to reverse that process and just get, well, essentially what we want to get is all of that same information again, so that we can squirt it back through the encode function, but with a different bit width. So we want to round trip it from a 32-bit integer to a rational number, and then to a 64-bit integer approximating that rational number. Which is fine. It just means I'm going to have to write some more code, but that's pretty much what I've signed up for, isn't it? Is to write code. Okay, fine, let's do it. I foresee a problem here because we've got infinities and nans, which you can't turn into a numerator and a denominator because they haven't got one. But let's cross that bridge when we come to it. I think I can probably do these ones, and then we're going to have to think. I think the thing I wrote here, float RB, this thing is going to need to be necessary, because at the moment we're passing in the things that you need to encode a normal number as a float. But if we need to be able to round trip infinities and nans and stuff, then we need to have the ability to call different methods. And I think probably polymorphism is the answer here. Like, rather than for decode, I'll implement decode now to just return whatever parameters encode needs. But I think ultimately what we need is for decode to return an object that might be a nan or an infinity, and then we can just call encode on that object and just tell it how many bits we want. And it will already know, if it's a normal number, it will know its own numerator and denominator and whether it's negative. And if it's a nan, it will know what its payload was and so on. Ufuk is saying, can't you treat infinity as a rational with non-zero numerator and zero denominator, and nan as zero numerator and denominator? That's interesting. So yeah, I guess you're suggesting that, like, yeah, that I can sort of do some sort of in-band signaling with the numerator and denominator. Sorry, I'm just going to finish that thought before I answer Chris's question. Yeah, I guess that's another option, is find a way to encode nans and infinities using a numerator and denominator. I mean, firstly, I feel a little bit icky about that, which is not a very scientific position. The practical problem I can see with that is that nans have got a payload and that needs to live somewhere. I mean, maybe there's a different arrangement of what you said that could use a payload, you know, could hide a payload. ultimately I'd rather be explicit about it if I can. Anyway, this whole thing's a digression because I've got to get these ones working first. Yeah, exactly. It's the yeah, I mean, because there is some redundancy in the sort of in the state space of these rationals isn't necessarily an excuse to try and squirrel away nans and infinities into them, but I think you're completely right that it could be done that way. Zeta, you're asking about this. We have not seen this before, except this was something I made a little note about. So this actually isn't it's not actually a value. It's a special piece of syntax for the interpreter. So I did spot this briefly many hours ago. So the values here for the result in an assert return, it can just be a conventional number, but which is what const is, but which is defined up here. Sorry. So, i32.const 42. It can also be this numpat, which is specifically either a number or one of these two special syntaxes. And I remember I made a note. Assert return has an extended syntax for its expected value, which allows it to match particular kinds of nouns. So we can't just evaluate the expected value as a normal WASM expression, even if we want to. Now, that is currently what I'm doing. In the interpreter, I am just evaluating to find the expected. Yeah, there it is. I am just evaluating it. That is going to stop working as soon as we get down to that. And that's going to necessitate a sort of case expected here where we sort of say, well, if it's f32.const nan canonical, then there's like some other case here. And then this is the else case. But again, we will have to deal with that in a bit. What the hell was I doing? Okay, what I was doing was worrying about... Oh, stop it, Siri. Worrying about implementing this, because the way that we need to implement this is we need like a decode. So after this encode, or maybe I'll do it before. We just pass in an integer and I guess a bit width. These to-dos really belong down here, don't they? So this is going to be, determine numerator. I haven't even thought about what this needs to do. I kind of knew what the skeleton of this function was because I stepped through it last time with an example. But this is going to be like calculate numerator and denominator and sign. And then this is going to have to return numerator, denominator, negated. And then I guess in here, we're going to have to implement f64.promote f32. So this is going to look like promote f32 value. It's going to set, like, we want to write code. Let me just check that this makes sense. So this is f64. So let's do the usual thing where it's like raise unless bits equals 64. So So what I'm thinking here is that we need to decode the value, and we are specifically decoding it at 32 bits because the input is 32-bit and the output is 64-bit. So we're saying decode this as a 32-bit float. So this is a little bit dodgy because this isn't really a float. This is an integer. Let me see if I can get away with not doing that. And then we want to encode that. Oh, but that's going to be... Yeah, we don't just get a... Okay, right. We don't just get a nice tidy object back from that. We get numerator. Well, at least that solves my naming quandary. So we get numerator, denominator, and negated back from that decode operation. And I guess this is what I'm saying. What I was saying is that, like, really it would be nice if they were just wrapped up into an object that we could then call encode on. But that's, I'll do that next if I can get the actual decode logic working. And then what we return is we then encode. So again, this is like round tripping that. For some reason, this is a keyword parameter, and then bits is 64 in this case. So that's right now, that's what I think the API is going to look like. This is what the implementation is going to be, basically. Oh, no, I think it's better when it's wrapped like that. But obviously that is not going to work because we have... Oh, thank you for warning me about that, Ruby. That was definitely a typo. Right, okay, yeah. The slight issue is that I haven't calculated what the numerator or the denominator or the whether it's negated is. Okay, so this is... So I hadn't thought about what this involved before, and that's why I was a little bit intimidated by it. But actually, this is just yanking stuff out of... This is just yanking bits out, isn't it? Like... Like the denominator can just be... It really depends on what the exponent is. Yeah, it's sort of the opposite of... Yeah, it's a good point, Afuk, that really the denominator is basically always 1. But I think in this case it's not going to be. Like, in fact, I think the existence of this decode function is the thing that justifies the denominator here, because what's going to happen here is that we're going to say something like fraction equals something, exponent equals something, sine equals something, negated is, sine is non-zero. That doesn't return a Boolean, does it? And then we need to turn those into numerator and denominator. And so depending on whether the exponent is positive or negative, we need to make either the numerator or the denominator larger. So because the exponent could be a negative number and, you know, the decoded number that we're returning here might be very small, we need to express that as a ratio between two integers where the second one is something other than 1. So I think we are going to need, in order to represent this, this is sucking stuff out of the encoding, but then we're going to have to convert that into numerator and denominator, which is essentially the sort of the inverse of that process that we've already implemented. Okay. So how do I do this? This is like mask off the bottom 23 bits. Oh, and then if I... Right, so if this is integer... and then the mask would be 1 shifted left by 23 minus 1. Yes. Okay, well, these 23s are not right. Should be... Okay, look, I'm just going to have to copy this because I need all of this information again. So yeah, this, you know, this needs to go into like a precision class or something so that I can just say, I mean, maybe this, instead of having a bits argument, maybe you should just pass in like a rich precision instance that knows how to answer all of these questions. So this 23 is fraction bits, and this 23 is fraction bits. Oh, and this was... I actually wanted to, you know, shove it off the end. I think that's a bit nicer. So it gets it's encoded, and then we pull out the bottom fraction bits. I think that's right. I mean, maybe I should copy my mask helper, because this is really just masking the bottom bits off. But so we take the bottom fraction bits and then we throw them away by shifting them off to the left, to the right, sorry. And then we do the same thing again here, but this time it's exponent bits. And then same thing again. And then the sign bit is just the bottom bit, which should be all that's left at this point. But we can just mask that off. So that's how we take it to pieces. Again, I'm just sort of splatting out code here, and I don't have any kind of I don't have any way of running this because I don't have a unit test. Should I write one? Let's try. I mean, it's sort of tempting to just to just copy these, but I don't know if that's gonna... No, it's not going to give me the same answers because it's going to give them to me in base 2. The exponent will be in base 2 rather than base 10. Maybe this one. Well, what's the easiest possible example? I guess this one. So if I decode so it's going to be 32-bit, and what I'm expecting is to get I guess the numerator is 0 and the denominator is 1. And the thing that I'm decoding is the 0. So this is sort of, it is sort of the inverse of this, actually. There was a brief temptation to sort of make this thing into the forward and reverse assertion, but because the numerator and denominator you're going to get back are going to use the powers of 2, it's not going to work in cases like this one. So I'm just gonna take this a small step at a time so that I don't lose my grip on reality. So here we're saying, like, this is essentially, it's like expected numerator, expected denominator. Oh, there's like an expected negated as well, isn't there? False. Oh, what a mess. And then this thing is encoded. And so this is going to say decode encoded bits. And instead of actual, it's going to be actual numerator, actual denominator, actual negated. I can't be bothered to write all of that. So let's just say unless actual numerator, actual denominator, actual negated equals expected numerator, expected denominator, expected negated. Blimey. Right. Yes. Okay. So at the very least, that's running that code. I mean, whether this assertion is correct or not, I don't know. But that gives us a way of running this. So how am I going to recover the... Once I've got the fraction and the exponent and the sign... Well, I've got negated. I need to recover numerator and denominator. I suppose the thing is, I've got the fraction, and I need the significand. Like, so if here I say to do compute significand, then once I've got that, then I can just say if exponent is negative, then numerator denominator equals something else. Numerator denominator equals something else. And the reason I'm sort of separating it like this is because if the exponent's negative, well, let's do the non-negative case. So if the exponent is some positive number, then the denominator is 1 and the numerator is just the significand times 2 to the power of the exponent, because that's what the exponent means. However, if it's the other way around, then the significand is the numerator and then the denominator is 2 to the power of, not the exponent, because this is a negative number, but the absolute value of the exponent. So this is what I was talking about. If it's a small number, then we put a big integer in the denominator. If it's a large number, then we just make the numerator even larger. I haven't done anything about the compensate for exponent bias. But once the bias is applied correctly, then I think this is going to give us the numerator and denominator. The significand is just the fraction with the hidden bit set to 1. So that's just fraction or 1 shifted left by fraction bits. So it's like past all of those bits and then a 1. I think that's right. Now, adjust for exponent bias. When we do encoding, we add the exponent bias onto the exponent that we actually mean. So I think when we're doing decoding, we just remove it again. Is this right? Let's try running it. Unhandled exception. Well, so it didn't return the right numbers. It would really make things easier if I just called this actual, wouldn't it? Because then I can raise actual dot inspect. Oh no. Well, that's not correct at all, is it? What have I done wrong? Let's see what comes out of this. I think I'll look at all of these in binary. I'm sure I've just made some kind of silly mistake. Well, obviously I've made some kind of mistake, but I'm asserting that it's a silly one. You also need to compensate for the exponent fraction bit's initial value. That is correct. I had forgotten about that. Right. So, yes. So we not only subtract, thank you, Afuk, that's exactly right. So not only do we add the exponent bias to the exponent, we also, by initializing it to fraction bits, we add that to it as well. So we need to remove that as well. Oh, I'll be so happy if that turns out to be the... if that just makes it work. Oh, why didn't it make it work? I mean, it's given a different answer. I'm sure that this is the problem, though. I think you're right, Afuk, that this is what's caused the problem. I mean, maybe... Let's just do some puts debugging. So decoding, encoded, well, let's say sprintf. So this is going to be %0, however many bits in binary encoded. hold on, what am I doing? Close bracket, close curly bracket, close quote. Oh yeah, this is a 0. Yeah, you're right, Afuk. I'm sure that's the problem. That. Yeah. Okay. All right. Well, let's puzzle this out. So what's going to happen? How do we detect zeros? I guess it's at this point, isn't it? Like, because what we get is like literally raw zeros in the exponent when it's a 0. Yeah, it's this that's the problem, isn't it? Like, I just plonked the hidden bit in there, but actually... So what does this look like? If I say the hidden bit is exponent dot 0, 0 or 1, is that enough to just make it magically work? Well, the answer is sort of, because this is actually the correct rational number. It's just not the one that the test was looking for, because the test was expecting to see 1 in the denominator here. Obviously, the denominator doesn't matter when the numerator is 0. So maybe we could be a little bit more... I'm just going to back out of this and think about it again. So if the exponent is 0, then like do something special. Otherwise, we definitely want to do all of this. I think we always need to knock off the exponent bias, because that's just part of the encoding. Is that right, though? Maybe not. Maybe if the exponent's 0, maybe we want the significand to just be whatever the fraction is. Because if the fraction's 0... Because, okay, if the exponent's 0, so this is either a 0, which is 0 fraction, or subnormal number, non-zero fraction. So either way, we want the significand to be the fraction without this hidden bit set, because zeros and subnormals have a 0 as that hidden bit rather than a 1. So it's just literally the same as the fraction. What's the fuck saying? Fraction bits also don't need to be compensated for subnormals. Yes. Right. So yes, we don't need to do this fraction bits adjustment. Well, no, we do. For subnormals, we do, actually. For zeros, we don't. So if significand is non-zero, this means we're subnormal. Well, in this case, we definitely need the exponent bias, because that's meaningful for subnormal numbers. For zeros, not so much. And I guess what we would like is for like the canonical exponent for zeros to be literally 0. So we're like not going to touch it in this case. But we do also need to adjust for the fraction bits. But I think it's one fewer, because a subnormal number is inherently not... I mean, maybe we don't need to worry about any of this because we're not trying to implement this yet. But my thinking is that a subnormal number is not a 24-bit number at all. It's like a 23-bit or smaller number. So when we compensate, it's not like 1 point something. It's everything to the right of the decimal point. So it's because it's only a 23-bit number, we only need to subtract 22 from it here. But I'm going to leave that commented out because I think probably this is enough to make the test pass. Yes. So I don't think this is really adding very much. I'll leave this commented out because we haven't had to deal with subnormal numbers yet, but I think this definitely makes that test pass. Let's see what happens with the old conversions.wast. Okay, so we did get past positive and negative 0. This looks like a subnormal to me. Let's just check that. Like Ruby doesn't support that syntax, but it's 1 times 2 to the power of minus 149. So this is our value, or encoded. What does this look like as a 32-bit number? What am I? Why am I confused? It's because I need this to be... I need to pack this as a float and then unpack it as a long... Okay, so that is the smallest number. That's the smallest float, and it's subnormal. So, well, I'm not going to race ahead. I'm going to make a commit because I have actually got something working. So what is this? All that stuff. Not all of that stuff. Don't want those to-dos. I guess I'll leave that comment in. Oops. So this is begin implementing Wasmina float decode and test 0. I think that's that commit. Yes. Okay, but we do now need to think about how this subnormal is going to work. Let's write a unit test for that. So let me just give me a second to get my head around what the hell we're doing here. So this looks like, yeah, unsurprisingly. So I want this to, the number that I am decoding is this. So all zeros with a 1 on the end. And the number that I want that to be is 1 times 2 to the power of minus 149. So that means that the numerator is 1 and the denominator is 2 to the power of 149. Is that right? I mean, of course it is, but I feel adrift in basic high school, or not even, mathematics. Okay, yes, that is the same thing. So I think this is legit. I think I should be able to decode this 32-bit float and be told that that's 1 over 2 to the power of 149. That seems perfectly reasonable. Right. But I don't get that. I get 1 in the exponent, essentially. 1 in the denominator. And that's because I haven't made any attempt to adjust the exponent. So this was what I penciled in. Let's see what happens. Oh my goodness. Okay. I guess that's right then. Shit. Oh. Again, I could have added that. I'll hook it up in the next commit to the interpreter. So I guess this is support subnormals in Wasminer float decode. Let's just say for zeros, the exponent really doesn't matter, but we're leaving it as literally 0 because that's a nice canonical default. For subnormal numbers, though, we need to adjust the exponent to account for both the bias. What order do we do it in? Well, I want to say bias first, and the encoding format, i.e. the entire significand is a fraction. Okay. Let's run the acceptance test again. Ooh, we got quite a long way. But not all the way. Okay, but I think I deserve a commit of this. So let's say I mean, that pretty much is going to be the implementation of that instruction. It's just that it doesn't, the thing that it's using doesn't work properly yet. So this is specifically F64 promote F32. This doesn't work for all inputs yet, but it will work once wasminer float decode supports everything properly. So we still haven't hit these canonicals, but I suspect we might have hit the infinity because I haven't thought at all about how to support that. Let's have a look and see which. Again, if only I had line numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 of them are passing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Indeed, it is infinity. So I guess that now I have to make a decision about how infinity is going to be represented. And I think I'm going to go with my previous suggestion of using polymorphism, because if instead of returning this triple of numerator denominator negated, I'm just returning some mystery instance that plays the role of a float and that supports the encode, I can send the encode message to it with a number of bits and it just works, then that gives me the flexibility to be able to return instances that aren't a package of a numerator and a denominator and a sign, but instead are a package of, in the case of infinity, just a Boolean that says whether it's negated or not. So that's like a whole thing, isn't it? What's in my diff? I'm just going to stash all of that for now because like everything is sort of working, and those are just making it more difficult for me to make commit. So I'm gonna attempt a refactoring now, which is to say, well, let's start with the unit test because that's how you do computers. I think this is interesting. So I need to come up with some API for actually constructing the thing that I'm going to call encode on in the first place, right? Like I want to do something with numerator, denominator, negated, and then I just want to call encode with a number of bits. So this is going to be like foo. And then this thing here instead of getting numerator, denominator, negated, it's just going to get This is getting a little bit hairy, isn't it? But this is going to get an expected, and then it's going to get an... Maybe that's okay. I'm actually not sure what I want to happen here. Let's try and do it forwards first. And then I'll think about what it looks like backwards. But I think this is right. That I just want to break... I just want to stage this computation. Basically, I want a factory here. So this is like for rational or something. And then that existing encode method is just going to be a method on whatever instance I get back from that. Let's just call this foo for now, so that because I'm getting distracted by thinking about what I want that to be. So let's just say def foo. So this method here is going to move into like a foo class. And conveniently, I can now make this method private. In fact, the way this is going to work, I have just decided, is that foo is going to be a struct that contains the numerator, the denominator. In fact, I don't, for now, why don't I, because I can just call the constructor of this thing. I do want to have a factory, but let's make this new. So I can make a new one of these instances, and then I call encode on it. So this is just staging the computation, like I said. Negated, keyword init. So this is just going to make a numerator, denominator, negated. Let's call this finite, because that's what I said in my comment. I know I said I didn't want to think of a name for it, but that's better than foo. So we make a finite float, and we've got a numerator and a denominator, and whether it's negated or not. These are all now keywords, which I suppose is a little bit satisfying. And this code should be essentially unchanged now, except this method no longer takes those arguments. Just takes a number of bits. Just have to be careful about local variables now, because we've lost... I think there were places where I was updating those local variables. So let's, well, instead of thinking, I'll just run the test. But yeah, numerator. I guess the problem is that these local variables get created where's that? Line 98. Undefined method divide for nil. So that the numerator that's been passed into scale significand is nil. Oh yeah, because this looks like it's introducing a new local variable called numerator. I think, I mean, obviously I could just put self.numerator there, but I think maybe, you know, inputs that I removed, the parameters are a numerator and denominator and negated as well, but that doesn't get changed. But I think if I just do this, that should fix that problem. Yes. In fact, I can do this, can't I? Check me out. So that's maybe a little bit grim. But that's what I'm going to do. I'm going to do it down there. Okay, I mean, this could do with being cleaned up a bit, but I think that essentially does what I wanted to do, is that it's moved that encode method onto some instance that can then be created by this decode method. But what does that look like for the unit test? So what does this look like? So we've got encoded that this gives you back, or will give you back, especially if I make it give you back, finite.new, numerator, denominator, negated. So now that's just an object that you can call encode on. Does struct have like values at? Can I just pull those values out? Does it not support? Is there one that lets you use the names? Maybe not. Could use deconstruct keys. I'm just not sure what the assertion is here. Let's just say actual numerator actual denominator, actual negated. Okay. And I'm not calling it. Okay. I mean, that'll do. So this is, I think that's a fairly straightforward, like extracting a class, essentially, refactoring. But I expect that that's broken, yeah, because I'm calling that in here as well. So what do I want to do here? And then this is encode bits. And then this is, again, finite.new. Negated false. Encode with the right number of bits. And then this, oh, well, this is rather nice because that means I can just call encode bits on the object I get back. So that code becomes way nicer. Great. I'm not happy about this code, well, or any, even, I'm also unhappy about the unit test knowing about it, but I'm even more unhappy about this code knowing about the existence of this finite class. I think I should have a factory where you just pass in a number and it instantiates finite using a denominator 1 and decides whether the thing is negative or not, but I'll do that next. Because this is the sort of hand over hand improvement on where I was. So this is extract wasmina float finite class and move encode onto it. We need to support decoding infinities, and we can't do that while we're representing floats as a triple of numerator, denominator, and negated. Having instances of user-defined classes will let us store whatever we need to inside the instance, and we just have to arrange for encode to do the right thing in each case. Polymorphism. It's just a little celebration there of, oh, I hate that. This is one of my least favorite edits I ever make, is moving a word from the end of the line of a commit message so that it doesn't have an octothorpe at the beginning. So, okay, like I said, I sort of want not for the unit test, but for this, I want like a convenience method called something like, it's like from signed, maybe. Just maybe from integer, that just passes in this integer, doesn't do all of this. Because I really don't think that anything should know about the existence of that class. Like, you should just be able to say, look, I've got an integer, can I please have the corresponding float at a particular bit width? And these things don't have an inherent bit width, and they're just the best representation of a rational number, and then it's only when you encode it that you have to worry about the width of it. So let's implement that. It shouldn't be difficult. I'm not going to bother writing a unit test for this. So let's say def from integer, I believe is what I called it. And that is just going to be finite.new. Numerator is the absolute value of the integer. Denominator is going to be 1, and negated is going to be whether the integer is negative. Does that work? Undefined method from integer. Oh, I just hadn't saved it. Okay. Okay. I mean, I like that more. I think that's a better API for this to be using. You know, it's sort of irritating that I haven't written any unit tests for it, but this is the guts of what I'm worried about, is the nuts and bolts of, you know, numerators and denominators. So I think I'm going to, yeah, I'm going to let that go for now. Like, for example, this test can't go through that factory method because it's providing a non-integer float. All of the rest of these actually have, all of the rest of these ones have got, are integers. They've got 1 in the denominator, but it just doesn't, it's not important enough for me to worry about. Introduce Wasminer float from integer factory. So I'm just going to say this is a much nicer interface for the interpreter to use when requesting the equivalent float for an integer. Okay, all right, but what was the point of all of that? I hear you cry. The point was so that I could implement this infinite thing. So I'm going to need to detect that. I've now got the machinery to detect it. Not detect it. I've got the machinery to return something that represents it. You know, which is going to be a struct that just knows whether it's negated or not. And then this is going to need some implementation of encode, which is not particularly hard to write because that's just whacking bits together. But how do we know? Well, we know if the exponent is large enough, right? So here we were checking whether the exponent was 0, but we also need to check if the exponent is like the maximum exponent. So that's just going to be, again, 1 shifted left by exponent bits is going to give us the next number after the largest possible exponent. So now we're in here, we're saying either infinity or nan. I mean, it's sort of interesting because once we're at this point, all of this guff about the, you know, the numerator and the denominator is irrelevant because we're not going to be making an instance of finite anymore. So I think this is going to be something like, you know, return infinite. Obviously, we need to think about nans, but for now, I think I can just say that. Let's see what happens. Yeah, got nil. Because of this. So how do we encode? I'm going to see how much of this I need to cannibalize. So there needs to be something in the middle here. And then at the end, we're going to do something like this. So for infinity, the fraction is 0. So I think maybe this. And we're not worried about the exponent bias. But we do need to know that the exponent is all the ones, which is what I just said here. Yes. All right, great. So that's set both the... I think that's both of these have worked, because this is just filling in... yeah, we need the exponent bits. We need the fraction bits. But we're just leaving the fraction as 0. Okay, great. That feels like a commit, doesn't it? Support infinities in Wasmina float decode. Great. Obviously I need to do something about this, getting the exponent and the significand bits from the overall bits, but I will sort that out later. And then we just had, okay, so we've got a different problem here, which is the non-canonical thing. So I'm going to have to do the thing that I just said that we were going to do, which is here, we're going to say case expected, because it's, and then this here is going to become the else case. Actually, this here, we need to remember that this is like success. Oh, but we don't have the actual value yet. Okay. So the reason I'm doing this is, well, firstly, to check that everything is still working. Okay, that's fine. But what I'm looking for here is the opportunity to, there won't be an expected value, or at least not one that we're going to compare for equality, because what this is going to be is, what is it in this case? F64 const nan. So this is going to be either F32 const or F64 const. That's going to be the instruction. And then there's going to be something like nan canonical, or I can see here there's nan arithmetic. That's going to be the nan pattern. I'm just nabbing this because I can see that I'm going to need to know how many bits wide the float is, because, or do I? Do I care about that? Oh yeah, I do. Because I need to turn the actual value into it. So I need to do wasminer float decode Do I need to know this? What do I want to do here? I've already got the actual value. Oh, but that's going to be an integer. So I need to, yes, so I do need this. Okay, yeah, sorry, I was being slow. So here I need to, in order to decode the actual value, surely I need to know how wide it is. Yes, of course. So that's going to have a width. So that's going to give me one of these wasminer float instances. And then what I'm doing is saying that success is that that is a nan. But I don't have that method yet. Okay, I'm going to cop out and use pack and unpack for now, just to make this assertion work first, because at the moment I don't have a way of asking if a thing is a nan. I don't even have that class yet. So, but I can do this with Ruby. I can say float equals actual value. I can pack that with some format, and then I can unpack one it as a float, and then I can ask, and then success is whether that float is a nan, and then here there's a to-do, like care about canonical versus arithmetic, whatever that means. Check whether canonical or arithmetic is what I mean there. Oh God, this is yet another place where we need to know the format strings. Okay, I'm just gonna bodge this in for now. And you know, this will be a cautionary tale for other programmers to be less bodgy than me. Okay, so if this is 32-bit, I want to pack this integer as long, 64 is quite long, 32 is float, 64 is double. Expected nil. Oh, it's just this. But let's say actual value equals nan. Oh, not actual value. Expected value. So that's just for populating this exception message. Expected nan canonical got this thing. So now we have to support nans in here. And the way we tell whether this is a nan or not is whether the fraction is 0. So if it's all zeros, then it's an infinite. Otherwise, it's a nan. And if it's a nan, then it does have a negated, but it also has a payload, which is the fraction. I think that comment has stopped earning its its place. Yes. I mean, I suppose arguably I could have implemented both of these with the same class. But unfortunately, the class that I would need to do that is the one that I haven't implemented yet. So just going to have to do it. So let's put this first. Nan. So this is payload and whether it's negated. That's not right. So for this, we do need the fraction bits. And the fraction is going to be, instead of the significand, it's going to be the payload. Don't really need to mask it off here, but let's do that anyway. Oh. Just realized this needs to be called nan. Okay, hold on. What the hell am I doing? I'm getting confused is what I'm doing. Okay, undo, undo, undo. Okay, that was all quite good so far. I just got confused about what I was editing. So, payload negated. This is basically the same as infinite, but it's got a payload. Great. I'm not sure why I put that before infinite. Sort of feels like maybe it should go after. Yeah, it's the order that they appear in there, and it's kind of, this is like a more sophisticated version of infinite, and then finite is everything kicks off at that point. So what did I say? Support nans in Wasmina float. Oh, hold on. This is really a separate change. So this is support nan canonical and nan arithmetic in return command. Right, and then this was support nans in Wasmina float decode. All right. Oh God, we're so close. It's after midnight, but I'm gonna look. This is so near the end. I've really just got to implement demote F64 because I think I've already got a reinterpret. Okay, let's look at this. What does demote F64 do? I don't already have a demote, do I? No. What does it do? I don't know. I'm just going to start implementing it. Demote F64 value. So is this just the opposite? Yeah. So this is saying just take a 64-bit float and try to approximate it as a 32-bit float. So let's see what happens if I just do the naive thing here, which is decode the argument as a 64-bit float and then encode it as 32 bits. I think the fact that we don't have any subnormal support in encode it feels like something that's likely to cause problems at this point, but let's see. Expected 0 got minus. So a couple of these passed. So I am going to add that. So it's F32 demote 64, right? So this is implement the F32 demote 64 instruction. As before, this isn't yet, but we just need to fix Wasmina float until it does work. Like, I think this is a very natural implementation of that operation. We just have to figure out why our code is not doing the right thing. Although it clearly is in these cases. Expected 0 got minus. Yeah, well, like I was saying, this feels like this is going to be a subnormal number, and then this is just 0. How are we going to make this work? Let's this is a disaster. I don't know why I was just sort of hoping that I could somehow magically get back my debugging code, but I think it's, maybe I can just copy and paste it. It was this that I wanted, this thing from inside the scaling loop. So, you know, this exponent is way too small for a 32-bit float, because the smallest exponent is minus 127. So what we need to do here is, well, firstly, we need to stop this loop before the exponent gets too small. Like right now, it knows the minimum and maximum significand. But it also needs to know the minimum exponent and the maximum exponent, so that all of these can be, like, this is about to reduce the exponent, and so for that to work, the exponent needs to be larger than the smallest it's allowed to be. And I mean, we might as well do the sort of symmetric thing here. That's wrong. Less than. So we're not only checking that the significand is in range, but we're also checking, or that, you know, that the significand is still out of range. We're also checking that there's still wiggle room in the exponent, because if we've hit the largest or smallest permissible exponent, there's no point in continuing this loop. We've already reached the largest possible value or the smallest possible value of the exponent, and so we just have to stop and make the best of what we've got at that point. And that might mean making an infinity, or in our case, I think making, well, trying to make a subnormal number. But I think in this case, I think what we can rely on is that the significand is still going to be 0 at this point, because this number is so much smaller than what you can express in a 32-bit float. I think the exponent, well, we saw before that the exponent was having to get much, well, smaller in order to accommodate the fact that this numerator was becoming absolutely massive. So I think the significand is probably 0 at that point. So I think we're going to get for free the behavior that we want, which is that this kind of becomes a 0. But in order to do that, we have to properly support the case where we have to deal with it properly when we've hit this, like when we've hit this limit. So what do I want to do? I think all of this is correct. I mean, let's just see what the debug output does. What I'm primarily looking for is to see that this stops before it gets to a ridiculous... Oh, except I haven't told it. I haven't told it what the minimum and maximum... I have to actually calculate these, unfortunately. Okay, well, I know how many bits it is. So I guess the simple... Oh, actually, I've already got the exponent bias. So in the 8-bit case, the exponent bias here is 127. So the minimum exponent is minus 127, and the maximum exponent is 127. So in general, the maximum exponent is the exponent bias, because that's... when we add that on again, if the exponent is 127 and we add on another 127, is that right? Yeah, because if all the bits are, we need some headroom for when we set all of the bits, because that means infinity or not a number. Yes, okay. And this... I think what we're going to need to do here, my gut feeling, is that we're going to need to stop short of this. I think if we get down to minus 127, then we've gone too far. But let's see. Let's see what happens. Wrong number of arguments. Okay, yeah. Well, I need to pass them in, don't I? And I'm going to need to do the same thing here. Okay, so we've got down to this minus 127. But that's overshot, because this is a little bit hard to explain, or a little bit hard to verbalize, but what I'm thinking is, we want to stop before it gets to this point, because if we're in a situation where we need to express a we need to express a subnormal number, then well, let's see what happens. Maybe I'm wrong about that. No, the thing, I just haven't thought about how to verbalize this, but what we want to do is detect this situation by seeing whether after this loop has finished, then it's possible that this is still the case, that the significand is still too small. Did I pass the test? Are you saying this is a different test than the... Oh yeah, I think you're right. Yeah, how far are we getting? Sorry, I was so distracted by the fact that it was not right that I missed. Yeah, and also that output. No, you're right. Okay. So maybe I'm... Well, I mean, there's still a problem here. 8388608 got 8388607. That's a bit suspicious, isn't it? But this is a case where... I think this actually substantiates what I was saying. I think this is a case where we should be... Yeah, I mean, that's a good point, Afuk. I think I should probably do some kind of commit at that point. Yes. yeah, you're right. It's passing for the ones that need to be 0, but they're not going to suffer from the problem that I am worried about, which is that it's overshot. And it doesn't matter that it's overshot in this case because it's just going to end up as a 0 anyway. But I think the one where it's failing is a place where it's non-zero, but it's a subnormal. And I think in that case, we've like done one too many iterations of the loop. But let's so what's this saying? So this whole change is basically just like limit exponent during limit float exponent during significant scaling. Previously, the loop was allowing exponents to become arbitrarily large or small, which isn't allowed, which won't work. So we need to check. So we need to stop the loop if that's about to happen. I think the min exponent is probably too low. It's probably too low for subnormals, but it's made some of the tests for zeros pass, so I'm committing it like this for now. Okay. So let's have a look at this. What does this look like? Sprintf. And then this one is 607. Yeah. So what's happened here? So the difference between these two things is that the exponent it was looking for... Oh, actually, so this is not supposed to be... Oh, okay, right. So I think this is another rounding related problem, right? Where I think this is kind of a good example of why we shouldn't allow it to go one more iteration, because what's happening here is that I think we end up with something that rounds up to the smallest normal number. But because that loop is being allowed to run one more time, I think it's not rounding up. Let me just, I'm not explaining this very well. I'm also quite tired. Let's just see what happens to that test if I stop that loop one iteration early. Oh. Well, I've broken something else now. Expected 0 got 8388608. Oh, right. This is okay. Well, of course, I don't know if the other thing is working yet, but okay, right. Let me think about this. If we stop the loop before it hits that minimum exponent, because the minimum exponent has got special meaning, which is that the hidden bit in the encoding is no longer a 1, it's a 0. So we're not really representing a 24-bit significand anymore. We're representing a 23-bit one, which is all to the right of the decimal point. So when we are in that situation where we've reached the smallest exponent that doesn't have that special meaning, and the significand is still not large enough to suit our needs, then I think what we need to do is just stick with that significand, but then adjust the exponent to, in the same way as during decode, we had to adjust the exponent here for the same reason. I think we have to do the corresponding thing here when so after we've done all of this business, we've scaled the significand, we've rounded it. I think we need to say if the significand is still too small, if it's less than the minimum significand, then it's subnormal. And then I think we just need to make the exponent one smaller, leave the significand alone, and just bump down to the smallest exponent, which has got this special meaning that says we haven't been able to produce a 24-bit number in the case of a 32-bit float. We've got one that's smaller than that. And that's what set, and so without adjusting the size of that significand at all, just by setting the special exponent, which is the minimum exponent, which is essentially what this is doing. This is saying set the minimum exponent. Maybe that's clearer. Then I think that's not working, is it? Oh, I felt sure that was gonna help somehow. Oh, because the minimum exponent is not actually the minimum exponent. It's the that's a little bit misleading, isn't it? Maybe I should change the whatever. Subtracting 1 actually does work. I'd forgotten that I literally just changed this to be not the smallest possible exponent. Now it's 1 more than that. But yeah, subtracting 1 from it absolutely works. Loads of them are working now. Although, of course, we've now found one that is not working at all. Or maybe it's the infinity, though. Because this is the other... Anyway, look, I'm going to commit this. So let's say... set float significand and exponent correctly for subnormal numbers. We don't want to let the scaling loop scale the significand all the way down to the smallest possible exponent. We want to stop 1 short of that, keep the still too small significand, and just set the exponent to indicate that the number is subnormal. Oh. Okay. I think that this is probably an infinity. Is this 32-bit? Yes, that is an infinity. But instead we got this. Okay, so this is the opposite problem, which is, like I said, we've left some headroom. This was what I sort of hesitated when I was setting the maximum exponent. Because actually, just like this isn't the smallest possible exponent, this is one more than it. This is one less than the largest possible exponent. Oh, sorry, one less than the largest possible. Is that what I said? Because we need that headroom to be able to mark something as being an infinity. So I think the same logic applies here, where in the same way as we spot when we've made something too, when that loop has failed to make a large enough significand, I think we also need to check to see if we've ended up with something that's still too large, then we need to increment the exponent. What do we do with the fraction in this case? Because, I mean, again, is it already all zeros? I mean, maybe it is. It doesn't seem like we need to zero it out. There's this temptation to like manually set the fraction to be 0 here. But I guess we don't need to, because it's I think I'm going to set it to 0, because I sort of feel nervous about I'm not sure whether that can happen. I guess I'll comment it out because it's not necessary. Yeah, you're right. Fuck, they pass. However, I can't see any tests. The case that I'm concerned about is the case where, just like the numbers that are too small becoming zeros, I'm concerned about the case where a number which is too large becomes an infinity. And I'm worried that there might be, if there's any junk left over in the significand of that very large number, then this won't look like an infinity, it'll look like a nan. In fact, talking about that has made me feel like I just want to do it. So I'm just going to do it, even though I don't really need to. Set float significand and exponent correctly for infinities. I mean, that is literally what I'm doing. It feels like we're incredibly close. Expected nan canonical got this. So it's saying this isn't a nan. Oh. Right. Because so something is being demoted and we're expecting it to be I mean, maybe you're right, folk. Maybe they, I mean, I don't know if it's important, but maybe they should have one here where a very large number is being demoted to infinity. It's slightly surprising to me that they haven't got that, but I'll add it to my to-do list. Contribute a test case where a large F64 is being turned into infinity when demoting to a 32-bit float. Okay. So I think we're just in this business now, and I think the problem is that the payload is getting truncated. So the payload in a 64-bit NAN is canonically a 1 followed by lots of zeros. Yes. We've already dealt with, in fact, these canonical NANs are being generated by Ruby at the moment, because we're using pack. We're packing a Ruby NAN, but when you do that, you get this canonical NAN that's got all ones in the exponent, and then there's a single one at the top of the fraction. And the problem is when we round trip this and make it into a 32-bit NAN, this fraction will get truncated, and now it's all zeros. So I think we need we need to check for this when we serialize, when we encode a NAN. So this payload here, we need to make sure that we're not accidentally, like in the case where this masking is giving us only zeros, we need to make sure that we're making some effort to make it non-zero. So like we need some kind of whatever if fraction 0. And I guess the whatever is that we should probably just set the top bit. So if fraction is 0, then we should set one shifted left by fraction bits minus 1, because if it was fraction bits it would be off the top. So I think this is the sort of the safeguard against that, where it's like if masking the payload has given us something that no longer looks like a NAN, let's just set the top bit of the fraction to make sure that it's still nanny. Oh, they all passed. Okay. Okay. Yes. No. So this is always set at least one bit of a NAN. No, well, Afux asked, shouldn't the top bit always be set in a NAN? I don't think so. I think, well, let's have a look. My understanding is that it's an infinity. Sorry, it's an infinity if they're all zeros, and if they're not all zeros, it's a NAN. And I mean, I am aware of various architecture specific standards of like this thing here about quiet NANs and signaling NANs and how they're indicated, but my understanding was that it really doesn't matter. Yeah, like the biased exponent field is filled with all 1 bits to indicate either infinity, where the trailing significand field is equal to 0, or a nan, where it's not equal to 0. And then when you get into this quiet and signaling nans, they're distinguished by using the most significant bit of the trailing significand field exclusively. So I think if it's a quiet or a signaling nan, then you have to set that top bit, and then the payload is the rest of it. So maybe I'm using the word payload wrong here, actually. Maybe there's only a payload if the top bit is set and then the rest of them is the payload, but that seems like a minor problem for now when encoding it. This is a problem when demoting 64-bit nans to 32-bit because the truncation of the fraction causes it to become 0. By checking for this, we can make sure that at least 1 bit is always set, thereby indicating a nan rather than infinity. I think this is the last one. I mean, I know it's getting dangerously late, but I think this is the last one, because in this file, reinterpret was the last, and I think we've already got reinterpret. F32, F64. It looks like we need F32 reinterpret. Right, okay, so it's sort of the other way round. So these reinterpret F32s was just the identity function, because it was saying I want to interpret a floating point number as an integer, but that's how we represent them internally, so we don't have to do anything. I think here it's exactly the same business. So on the assumption that we're being asked to reinterpret a 32-bit integer as a 32-bit float, or a 64-bit integer as a 64-bit float, then we just return the original value. Yes! That's the whole thing. All right. Implement the F32.reinterpret I32 and F64 reinterpret I64 instructions. Like I32 reinterpret F32 and I64 reinterpret F64. These are just the identity function because we currently represent floats as integers internally anyway. Wow, okay. That feels exciting. Now, for my final trick, I can add some stuff to this. I can add conversions to the test script. Add conversions.wast to the test script. And also, I suppose I should add, well, what I want to do is this. Also run float test. I think what I'm going to do here is say for test in S expression parser test, float test, do, and then just, you know, make this work the same as the other one. Done. Does this achieve what I wanted it to achieve? Oh, this all goes to standard error, does it? Great. Yes, it looks like it is running float test. Great. I'll just amend that, that's fine. Okay. So now if I push this, then hopefully I will be rewarded. There we go. By a green dot. I will never understand how this decides what to expand. Whew! Wow. Fantastic. Okay. Well, I'm very relieved that that worked. All right. Well, I'm extremely sleepy, so I'm gonna wrap that up now. But thanks a lot, Ufuk, if you're still there. Thank you for hanging out with me and helping me work through all that, because you were a constant source of inspiration and unblocking, so I really appreciate that. And anyone else who is watching this live or after the fact, thanks for sticking with it. This has been by far the longest one, but I've got to the end of that conversions file. So I guess now, well, I think probably what I'm going to do next is some cleaning up. But the next thing to implement is to move on to the f32.wast that's got the basic arithmetic operations, and then there's a bitwise and the comparison ones, and just like flesh out some more of those float operations. But yeah, I think next time I'm going to permit myself to indulge in a bit of refactoring and see how far I can clean up what I've got already. There's also a temptation to try and use this implementation that I've got instead of pack and unpack, because now I've got my own fully controllable system for converting back and forth between IEEE 754 floats and rational numbers, essentially. So I might be able to sort of cut Ruby out of the loop entirely on that, which would be quite nice. So yeah, that's it. Thanks for watching. Yeah, thanks for your time and attention and patience. I will see you on the next one.